And we are live.
Okay, welcome and good day, everyone. This is our workshop on eVTOL crashworthiness, second workshop in a series. I'm Joseph Pelletier, the Chief Scientist for Crash Dynamics at the FAA, and our co-host is Justin Littell from NASA Langley. Next. So as I mentioned, this is a second in a series of workshops. The first one that we had back in April provided some of the historical basis for crashworthiness and some of the overall regulatory considerations that we were looking at. This installment is going to review crashworthiness from the perspective of professional organizations and stakeholders, and also provide some information on the regulatory approaches as they pertain to certification efforts with regard to crashworthiness for both the FAA and EASA. Next. So you all are watching this via a YouTube link. The speakers and the moderators, we are on as a Teams meeting. There's on the announcement, there's a conference IO link. If you want to click on that, there is a poll question where you can enter your name and email address to be provided with updates on future installments and other information. During the meeting, so the presenters will present, and then with the conference IO, you can use that to submit questions to ask of the speakers. The moderators will then go through those questions, and if there's time left at the end of each presentation, either Justin or I will ask those questions of the speakers. Within Conference IO, you can look through the questions that are being asked, and if someone has already phrased a question that you are interested in, it gives you the ability to upvote it and kind of vote for that to be one of the questions. It's unlikely that we're going to get through all of the questions that would be asked, but we have the ability to save them, and then we will save those for future discussions for future topics at additional workshops. In between each presentation, the questions that are asked will be cleared, and then we'll start over with a new series of questions on the with the next presentation. Okay, next. And this is a quick agenda. As you see, we have a series of speakers on a variety of topics. Start off with Vertical Flight Society. We'll have the representative from Gamma, Uber. We'll talk about some of the operations. Then get into some of the more regulatory, so both the FAA and EASA, and then going into ASTM and some of the regulatory framework that they are working on. I'll say that the presentations that we will have, copies of the presentations will be made available after the meeting through the conference website. And with that, we'll turn it over to Justin.
Thank you, Joseph. Good morning, good afternoon, everybody. I'm Justin Littell at NASA Langley, and I just have three very short slides as sort of an intro into our topics. That sort of give a very brief overview as to why we are wanting to conduct these workshops, and also, present this information so that folks that potentially are, not familiar with the topic can sort of see what we're trying to do here. So, I want to say the first is a case study that was a test that we had done at NASA Langley a couple of years ago now. And there's a video on, but this is just a picture of the test. And this is a 14-foot drop in our drop tower, given the equivalent velocity of a 30 foot per second impact velocity. And basically, the point of this is that a fall from only 14 feet, which is the height you see in that picture, has the capability of causing occupant injury if there are no protections available on the vehicle. So this particular test was from the Part 27 regulation, and while not directly applicable to eVTOL specifically, because maybe a difference in seat configuration, I just want to put the idea out there that these things don't have to have a very far way to fall in order to cause injury, and thus things like crashworthiness protection needs to be investigated. moving into some market demand, just to sort of show where the market is moving. There's a couple different studies that have been completed previously, some from NASA and some others. And basically, what it's boiling down to is the fact that using 2015 data, there's 714,000 flight hours. In 2035, there's 5.8 million flight hours estimated. There's a Boozell and Hamilton study, $500 billion market value in some of these scenarios of the VTOL market. Uber conducted some studies and basically assumed about 5,000 units produced per year in the 2030s timeframe, which gives you about 14 million flight hours per year. And then using some equivalent transport aircraft data, there's 18.5 million flight hours for 2017. So all this boils down to that there's tremendous growth in these vehicles in the upcoming years. And we're just at the start of it. And then finally, I want to talk about public perception. This is a study that NASA Crown Consulting conducted for NASA. And basically, it boils down to the fact that there is really there's 5 major concerns, and safety is one of those 5. There's a text in there that says, consumers cite proven safety records and demonstration as factors that would most increase their level of comfort. So knowing what the performance of these vehicles is under normal operations and also emergency operations is very high on sort of the consumer focus here. So there's 3 strategies that Crown suggests for public acceptance. One is technology, so establish the safety standards, focus on noise, which is not our topic today, but safety systems is. United messaging, that's address public concerns and emphasize benefits. That's and then proactive engagement with concerned groups. So these bottom 2 is a little bit of what we're trying to reach out today and focus on. And then finally, I'll just show an example, a more recent example. This was presented at the VFS Forum actually this year. And this is the NASA Lift Plus Cruise concept vehicle. There's 2 configurations of it. One is sort of a baseline non-energy absorbing configuration. What we found is we have an occupant model in there. We ran a 30 foot per second vertical case, just like the drop test I showed above, and we found that injuries were above the established limits. Once we started putting in some of this energy absorbing features, we have some hybrid carbon material, we have stroking seats, we have energy absorbing subfloors, things like landing gears and things like that could also be utilized. We did not do that in this test article, but what you can see is just by adding some type of energy absorption, we were able to bring the injury limits below the established limits now. So a very quick overview of why we're doing this today. Joseph, back to you.
Thank you, Justin. So, a question that comes up is, in crashworthiness, why now? What I'd like to say is that a lot of these vehicles are really, we're projecting forward, so they're early in the development cycle. So if you can get on the ground floor and start incorporating crashworthiness features, energy absorption, the space, the technologies that are needed, that will pay great dividends in the future because these airframes are likely to remain around for a long time. The other thing is, as Justin was showing, is when you look out in the future, the number of flight hours that are projected, you could go from that and say, we're going to have, some emergency landings, some incidents and things of that nature. So we have to expect that there are going to be some sort of outcomes that we're going to need to protect the occupants from to ensure continued growth and acceptance. It also hits one of the Crown features is getting the safety message out there, getting the public perception that these are safe vehicles, that they can maintain safe passage from point A to point B to ensure that continued growth. The other aspect is right now, the current regulatory framework is really based upon other designs. So we've borrowed the framework from other classes of aircraft, and we've had to sort of modify and mold them in place in order to kind of achieve the project basis and move forward now. As we begin to learn more about how they operate, the failure modes and things of that nature, we may have to change and modify some of those some of those regulations and means of compliance. But if you look at doing the system level safety performance now up front, we should be prepared for any changes that might occur going in the future. Yeah, next slide. So as I mentioned, this was the second workshop where we're going to have additional workshops planned. Probably later this year, we'll have our third installment, and it'll be one that we'll look at, we'll say, DoD issues and things that they're looking at there. Then early next year, we're going to look at one that's going to be sort of application focused. So it'll be maybe the research application, you know, what Justin was showing. Here's the kinds of things you can incorporate. We'll begin to look at what are some of those technologies and how can those be used and implemented to achieve crashworthiness. We are still hoping at some point to have an on-site face-to-face workshop where we'd probably do a quick review of the 4 previous workshops that we had, and then use that as a more of a discussion focused one where we kind of look at leftover questions. What have we learned through these series of workshops, and how could we move forward from there? We don't have a date or location or anything of that at this time. Again, that will depend upon travel and how things are going next year. I think that was all I have on the slide here for our introduction. And I forgot to mention, we're going to do the best that we can to kind of keep us on schedule. So we will try and we will follow the agenda as closely as what we can. Obviously, to get a little bit ahead, we'll allow some additional time for questions. But as we get moving through there, we will just keep moving along and hope to have us out of here on time. So with that, our first speaker is Mike Hirschberg from Vertical Flight Society, and he's going to be talking on enabling a safe electric VTOL revolution. Mike Hirschberg is the executive director of the Vertical Flight Society, international nonprofit that supports eVTOL and rotorcraft development. Mike is an aerospace engineer with nearly 30 years of experience and has led Vertical Flight Society since 2011. So with that, I will turn it over to Mike for this first session.
Mike, you're on mute.
You didn't miss anything because I was asking if you could hear me, so good. All right, so I want to talk about, we see this as an electric VTOL revolution. This is a technology that opens all kinds of new possibilities for aviation and mobility in general. But obviously, as discussed, safety is probably the key issue. Let's see. There we go. So as mentioned, we're an international professional society working to advance vertical flight, founded in 1943 as the American Helicopter Society, but our mission has always been all kinds of aircraft, all kinds of vertical flight aircraft around the world, manned, unmanned, everything. We're an educational nonprofit, so our whole purpose is education and expanding our knowledge and providing resources for developers, in industry, academia, and government, and moving forward to realize these advancements, not just in technology, but in adoption as well. We're a membership society, so everyone, industry, academia, and government's eligible to join VFS. So as mentioned, we were originally founded as the American Helicopter Society, and this is during World War II when most of the development was in high-speed, long-range fighters and bombers, and then this technology that could barely get a person off the ground, maybe 2 people, very limited in its payload and range and endurance and everything else. But the people developing the technologies, again, industry, academia, and government, needed to come together to help support this advancement. Similarly, we saw this coming in the 2013 timeframe. We held the world's first workshop on eVTOL. You can see some of the leaders today in eVTOL. We're at the first group. We found a room that held 100, and we sold out pretty quickly. And we've been working, ever since to try and lead and collaborate in advanced eVTOL technology. We have a lot of resources, and I'll go through some of these here in the beginning. It is available to everybody. There are certain benefits if you join as a member. You get more stuff for free or discounted. But we have an online library with actually it's an older number now. It's 14,000 PDFs of technical papers, conference proceedings. As Justin mentioned, we had our 76th annual forum this week. He presented a paper. All those papers are online and accessible. It's really the wealth of knowledge of the key developments of vertical flight over 76 years up to the latest. We had 230 papers published this week through our event, as well as our online magazine. I'll mention that, and we have a technical journal as well. So this is it's still primarily focused on helicopters and MAVs and UAVs, but still a lot of applicability to eVTOL as well. We have a magazine. I like to say it's the world's best magazine on vertical flight technology, and I don't just say that because I'm the managing editor and the publisher of that. But you can see just some of the topics we cover by looking at the covers of our magazine and of Vertiflight. So this is just a selected few, but it's advanced rotorcraft, eVTOL, even personal air vehicles, things like that for the Go Fly competition, etc. We started a website in 2017 because there were about 10 or 15 different concepts at the time, and we wanted to help provide understanding of what was out there and what was being developed. And so we started cataloging it. Again, this is keeping track of aircraft models, and we don't make any judgments on them. So it includes everything from the silly to the serious. We're a little bit backlogged now because we had the forum this week, but as of yesterday, we had 349 aircraft listed, and hopefully we'll get a few more up this weekend. We have it broken down into these different categories so that people can kind of get their arms around the different types of eVTOL aircraft under development. But people should remember it's 349 aircraft concepts. So Joby we show here with their latest generation air taxi, which is no longer called the S4, but we have the S2, we've got the Monarch, we've got the Lotus, so all the different designs that Joby has revealed, we have published. So there's really, of the 350 aircraft, there's about 250 companies or designers. Some of these are maybe just design studies by an industrial house or by students. But we do try to keep track of everything so that if somebody says, well, what was the Joby S2? You can go to our website and you can find out information about that. We also publish all of our Vertiflight articles on eVTOL on the website. So there's over 250 articles. A lot of them really, really in depth. We have 3,000, 6,000 word articles. We have the definitive story on Joby, for instance. And we keep that updated as much as we can. And there's timelines, videos. We've got a lot of resources. So this is the website, eVTOL.news. We also publish stuff on our social media channels. I don't have it listed here, but we have a couple of Instagram channels as well. So if you're looking for news, eVTOL News is a great way to find out information, in-depth information. There are now more eVTOL news sites, eVTOL.com, for instance. We work with them and a number of other ones. But we try to, provide a reference and helpful information for the entire community. As mentioned, we also have videos. So we have, hundreds of hours of presentations. We have short courses that people can purchase as a video on demand. Several courses on eVTOL design, eVTOL fundamentals. Everything that we can think of to help the community grow. As mentioned, we had our 76th annual forum this past week. It's helicopters and advanced rotorcraft, drones, MAVs, and eVTOL. We had over 1,250 attendees in our virtual event. That's 230 technical papers. We also had a lot of VIP panelists. We had a nice discussion yesterday with FAA, NASA, EASA, Uber, and Air Force on eVTOL developments and certification. Anyway, that's it. Since it was all virtual, people can still register and get access to all that and all the papers. We're going to have that up for the next year. So even if you don't see it live, you can still see, Justin's presentation yesterday, or I guess a couple of days ago. So we have our next eVTOL symposium. The last one we had about 500 people attend. We're going to be virtual here in this January. It's our 8th annual Electric VTOL Symposium. We're looking for abstracts for the technical papers. So the abstract deadline is in a couple weeks. There's a website. We've been having infrastructure workshops. We had a third one in September, and a lot of information on infrastructure. Both physical and operational ATM, UTM infrastructure. And then our next annual forum is going to be back on schedule in May. We're planning for Palm Beach. Hopefully we'll all be able to join and do that. And we also have abstract deadline for that as well. I mentioned Uber before, so we've been very happy to work with them. They're one of our members. They actually unveiled the concept of Uber Elevate at one of our, it was our fourth, I think, third eVTOL workshop, or Transformative Vertical Flight workshop in 2016. And we've been, Uber's been doing really phenomenal work and leading doing a lot of leadership activities on eVTOL. The eVTOL initiatives and working with partnerships across the spectrum. So it's not just the vehicles, which we're going to talk about today, but it's everything else. It's the infrastructure, the cities, the regulations, everything. And they've been doing a great job working towards that. And their mission that they're looking at is urban air mobility. And I'll talk about that here in a sec, but there's all kinds of applications for electric VTOL. Uber was planning to do some demonstrations, air taxi demonstrations later this year. I'm not sure that they're still on track for that, but they are saying they are still on track for certification and operational service in 2023. So we know when the eVTOL revolution is going to happen. We need to do everything we can to help to realize this great future that we see. I mentioned urban air mobility. That's just kind of one slice of it. There's a whole range from package delivery, personal flying devices, cargo, larger cargo, and then the urban air mobility and air taxis. There's also regional or rural air mobility. All of these are now kind of grouped under this broader term of advanced air mobility, or the Air Force had to come up with their own term, which is for Agility Prime, they're calling them orbs, but not a really great definition. And yesterday, one of the representatives from National NRC from Canada, National Research Council of Canada, said they've actually got IAM, integrated air mobility. So, we need more acronyms, I guess, but we just look at the technology, which is the eVTOL. And it's important to understand this isn't just electric helicopters. So, helicopters are phenomenal at hovering, and with a very large disk area, they're well suited to hovering. But when you want to take that horizontally rotating rotor and translate for forward flight, that it requires a lot of mechanical claptrap and a fair amount of complexity, which is cost, weight, and maintenance requirements. So trying to get rid of the complexity of rotors like the cyclic collective and swash plate. You see on the picture on the left, it's Sikorsky's electric Firefly project. So this is converting a small helicopter to electric power. You can see all on the floor is all the combustion stuff that you can get rid of. The engines, the fuel systems, the exhaust systems, things like that. So that sort of gives you maybe the first order of understanding of what it's like to why an electric VTOL aircraft could be much less complex than a helicopter. But that didn't eliminate the complexity of the rotor system, and that's really kind of the key way to get some of the advantage is to replace this costly, expensive, complex single rotor system with multiple simple thrusters. So most of the eVTOL aircraft use propellers. Sometimes they call them rotors, like multi-rotors. They're not rotors, they're propellers, they're fixed pitch propellers. But they can get off the ground and then get on a wing for efficiency. So a large diameter rotor or large diameter propulsor thruster is going to be the most efficient thing for hover. They sacrifice that by having smaller diameter propellers, but then getting on a wing for best efficiency. But one of the real things besides cost that could really enable this eVTOL revolution is they can be designed with much less noise, which really is an enabler for operations in cities where the population density is highest, and you can have this urban air mobility with much higher throughputs to have the aircraft in the air earning revenue as much as possible. And then there's a reduction in, a potential elimination for emissions and have a more sustainable aviation capability. So eVTOL aircraft are flying. They've been flying for several years now, actually 9 years, I guess. Some of the smaller ones are shown here. Kitty Hawk's no longer pursuing certification, or sorry, not certification, for operation for theirs. But both the Kitty Hawk Flyer and the Open-Air Black Fly have flown more than 20,000 flights, proving out the reliability so they could be used for private applications. So eVTOL aircraft are flying, but part of that, the fact that you can take a relatively small aircraft, you can put some electric motors, some batteries on there, and you can get it off the ground. Has really led to this what's called the Gartner hype cycle, where there's this huge peak, this hyper. People are almost hysterical about the potential for eVTOL, and we're still going up this peak of inflated expectations. But now we've been trying to get people to understand that there's it's much more difficult to develop an aircraft than just putting motors on it. There's the safety, there's operational range, there's all kinds of requirements or considerations people need to remember. And so we're trying to inform everybody, we're trying to educate everybody and bring everybody together so they can solve a lot of these problems. I mentioned before there's 350 concepts of about 250 companies or developers, and you look at the ones here. This is a graphic that we helped Aviation Week develop with our database. So the first concept shows the first column shows all the concepts. Some of these have actually been built to be large scale or full scale kind of proof of concept demonstrations. Some have gone into more advanced engineering or certification prototypes, and you have a couple now that have gotten to production of 100 aircraft or so. So just because there are a ton of designs doesn't mean they're going to be. Well, you have to understand where we are in the development. Because Otto Lilienthal said to kind of design an aircraft isn't really anything. To build one is something, but to make it fly is everything. But it's easy to design an aircraft if you don't know how. And the most important thing is to actually come to an aircraft that's in production and operation and is making money or meeting the needs of the user. So people know that it's a maxim of the aerospace industry that if you want to end up with a small fortune, you need to start out with a large fortune. Luckily, with the .com boom and other things, there has been a lot of money available for venture capital and ventures. So, but ultimately, it'll be successful if you can make money with these aircraft, both in sales and operations. So, low direct operating costs and seat mile costs is really the key result that you want to have. We know the batteries will continue to improve. You see some of the stats here, and these slides will be available, so you can go through some of the more details here. From a cost perspective, just first principles, eVTOL aircraft should be much simpler and cheaper to manufacture, fewer parts, much less complexity. And if they're cheaper, then you can and there's more demand for them. It'll be a virtuous cycle where you can produce them more mass production, closer to cars than handmade for helicopters. I mentioned before, noise is a key enabler. So with eVTOL aircraft, there's just a real potential for a step change in utilization through cost, noise, and emissions and other factors. So where are we today? So if you're a helicopter, if you're coming from the helicopter world, and you know some of the history, it was a long time after people got off the ground before the helicopter was actually able to do something useful in the 1930s. And then, they had some limited abilities in the 30s, but really the 40s and 50s. And maybe in the 1960s or so, they were really pretty useful, especially with the first turbine engine helicopters. So it's a much more compressed timeline today with developing eVTOL aircraft. But really, eVTOLs have been flying for almost 10 years now, since 2011. There were several designs that got off the ground then. Now we've got more advanced demonstrators flying, and it's really when these actual operational concepts are flying and starting to do passenger demonstrations and then getting to air taxi operations or other operations that they'll really finally be useful. And that's part of what we're talking about here today, is how do we get to that point where we have a capable product that the public trusts, that's able to earn revenue both for the producer, the developer, and the operators, and be beneficial to the public. So we see 5 key challenges for eVTOL aircraft for urban air mobility operations, and there's these are the key ones. But batteries, motors, the actual technology for the larger sizes here of 4 passengers plus a pilot. That's kind of at the ragged edge of what technology is able to do today, and also still keep the noise down. The infrastructure needs to be developed. Luckily, or thankfully, NASA and FAA have been working on the air traffic management solutions for UAVs and UAM. So UTM systems are being developed, which will be able to handle thousands of aircraft. Still a long way to go, but work is underway. There's a physical infrastructure. You see here a Skyport concept for Uber Elevate that Gannett Fleming, one of our members, developed. So there's all kinds of different ways or visions for the best way to have to maximize throughput, and that means it's going to be more benefit for us as consumers, that we'll be able to take air taxis when and where we need it and get there faster than if we had to take another available means of transportation. Standards and regulations are key. These are in development, and that's a little bit of what we're talking about today with the other organizations. I'll touch on that a little bit more in a minute. And again, safety, noise, not in my backyard, even if they're really quiet, and there's air pollution or visual pollution of, hundreds of aircraft taking off over my house or past my apartment. That's also something to consider. And if it's seen as a benefit where anybody can take it, and it's not just something for the rich, then that'll help with that public acceptance. Of course, we know that all these challenges could be solved with enough time and resources, but there is a rush. I'll say a rush. There is a push for first mover advantage to be able to get the best return on investment for the development of these aircraft and development of the whole ecosystem. Okay. So crashworthiness, so NASA has a couple projects. There's a revolutionary vertical lift technology, which used to be the rotorcraft project. That's really pivoted now to support to better support eVTOL and UAM. and it's focused primarily on the vehicle technology, so CFD and understanding the technologies and for the aircraft. Advanced Air Mobility, the AAM project, is working more on the operational challenges, and somebody from NASA can correct me if they don't like my definitions, but that's kind of roughly where they are. So it's important to realize that airplanes, as you see on the top right, airplanes crash horizontally. VTOL aircraft like rotorcraft crash vertically. So you look at some of the designs, and these are just notional designs that Uber came up with. But they're most likely to be unitized composite structures, lots of battery mass and distributed electric motor masses. So nothing like this has ever really flown before. On the bottom right, it shows the first testing that NASA with the Army and industry did of composite rotorcraft back in I guess that was in the late 70s or early 80s. So this was a new type of vehicle, and it needed to be tested so people could understand how to enable those. What does this say? Sorry about that. So it's time now with this totally new class of aircraft to be able to develop the understanding. And it's got to be an iterative approach to understand that. Let's see if this movie plays here. This is one of no, it didn't play. But it's there's been a lot of research. There was papers that were presented, as mentioned, by Justin Littell and Jacob Putnam. I guess you have to have a J to work on these studies. But there's studies underway, but it needs more empirical data. So Justin showed the crash tests from several years ago from 14 feet. We need more testing to be done. There's a lot of these ultralight aircraft. I mentioned Opener and Kitty Hawk and even EHang in China. I mean, they've all built over 100 aircraft. So there should be some that maybe at the end of life or whatever that could be tested. I'd love to see some of the companies developing aircraft do Space Act agreements with NASA and start doing some of these testing to understand how these aircraft react. Just like we did, here's a Boeing test on the right-hand side, testing airbags, testing a small helicopter impact with and without airbags. There's been other tests looking at the seats, as mentioned. Those are all very important, and it's going to take all kinds of technologies and a whole suite of design capabilities or take a whole suite of design approaches to make sure that in any case where an aircraft comes down harder than expected, that the passengers are able to walk away and everyone will be happy. NASA has you see it here on the right-hand side, has their lander facility. It's an incredible facility for dropping aircraft and other things, but it's expensive to maintain, and it's been being considered for mothballing. I think this is the time that NASA, the FAA, and industry should come together and start a new effort to understand eVTOL crash safety, to make sure that as we're designing thousands or tens of thousands or hundreds of thousands of aircraft over the coming years, that we understand what the design characteristics, the design methodologies are, to make sure that if there is or when there is an accident, that nobody has to learn the hard way how we should be designing aircraft. We need to design safety in from the beginning. So this session today is talking about professional societies. We started something over a year ago now called the Air Mobility Council. We brought together 10 or 12 different organizations. It's just an informal, discussion group really to try and coordinate and collaborate. Also working with the standards development organizations like ASTM International, SAE International. Please, we need the technical experts, we need the developers to get involved with GAMA, with this different associations, with the standards development organizations, to figure out what the requirements are. What should the certification and standards be? We, in our discussion yesterday, Mark Moore from Uber said, if there's one thing he could do to kind of get the professionals involved more, it's to work with the standards development organizations and the associations to develop these standards so we know, we can't expect the government to do it all themselves from their infinite time and wisdom. We need you, the industry, and academia, and everyone to get together to advance this. So kind of in summary, the eVTOL revolution we think is on track for 2023. I've been saying for a long time, there's 1,000 reasons why eVTOL won't work. We have to find solutions to all of them to find the path that does work to realize this vision of air mobility that we think is possible, and it's coming. Just a matter of when, not if. But we can accelerate it and have a much smoother transition if we all work together. So we all need to work and try to invent this new industry. They've heard the expression, it takes a village. Well, it takes a lot more than that. It's going to take society. It's going to take everybody from all walks of life around the world. It's going to take your help in making that happen. So that's my last slide. I'm happy to answer questions here.
Okay, thank you, Mike. I actually have one question for you, and I'm going to kind of paraphrase it a little bit. I guess it came in the last section, but given that your background in history with rotorcraft safety, and then VTOLs kind of being fundamentally different in how they operate, in that you may not have glide capability, you may not have auto rotate capability. Can you comment on what you perceive as safety differences, or is it maybe something that's a function of altitude, where maybe you have a dead space before you have another technology that might take over?
Sure. The answer is all of the above. So every aircraft will have to be certified to be safe and designed to be safe. As I understand, the FAA's certification approach is that if it has wings, it's going to be certified probably like using Part 23, like a small aircraft. If it's got a rotor, it would be expected to auto rotate and have those capabilities. And there needs to be multiple, there needs to be multiple safety nets. So that might be, not having the accident in the first place, would be, maybe there's lots of redundancies, or there's elegance of solutions. So if you have, maybe you've got wings and thrusters, you've got maybe batteries and an engine. Some of the other technologies here discussed, one thing I'm always appalled at is the landing gears, or that I've seen on a lot of these designs. So we need to have landing gears that absorb high impacts. Some of these are so dainty and elegant. I don't know what people are thinking when they come up with these conceptual designs. So it's absorption in the gear, it's absorption in the seats. Maybe there's airbags or crush zones or other things that can help with the impacts. I mentioned before having all the, where are the batteries? Where are the motors? Are they above? You probably don't want them right above the cabin. You maybe want to have them breakaway. So it's really a holistic design. And one of the issues I have, I guess, with the 350 designs that we have listed is that it doesn't appear that safety is really thought out as well as it should be to ameliorate all the different possibilities that could happen. So you don't have, as an eVTOL designer, you don't have a design until you don't have a complete design until the safety case closes, where you can ensure that it's not going to have an accident, and if it does have an accident, that everybody can walk away. So that's, and other people have looked at other things, parachutes or retro rockets or other things. So that whole safety, safety redundancy, or the safety net of different safety solutions is really, I think, going to be dependent configuration by configuration, and it's got to not only pass the muster of the regulatory authority, but also be even safer than that, pass the public scrutiny.
All right. Yeah, thank you, Mike. And then for those of us listening to us, is that we probably won't get to all the questions that are on here, but and then we'll see them cleared out after each section, but we are saving the questions so they can be addressed at a future time. So with that, I will turn it over to Justin to introduce our next speaker.
Thanks, Joseph. Our next speaker is going to be Lowell Foster from Gamma. And Lowell is Gamma's Director of Global Innovation and Engineering and is responsible for developing new paths for the integration of emerging general aviation technologies. His efforts include new ways to address certification and pilot training. And Lowell previously worked at the FAA as a flight test engineer, where he's responsible for a broad range of general aviation safety, policy, and regulatory activities within the Airplane Standards branch. All right, Lowell.
Well, Justin, thanks a lot. I appreciate that introduction. So today I'd like to build on what Mike shared with you, kind of the overview, and maybe plant some seeds to talk about opportunities that we have with a new generation of aircraft. I mean, it's a really exciting time. We are essentially building a whole new generation of aircraft, and we have a lot of opportunities with us. And I'd like to just maybe share some ideas. Key takeaways from this new advanced air mobility aircraft and small airplanes, you know, just traditional small aircraft. We've got a lot of opportunities in the future. I want to spend a little time to try to give you some of the rationale between the aligning certification costs with safety benefits, because the traditional dynamic seat approach doesn't quite do that. And if we really want to improve occupant safety, we need to really have an honest discussion and look at alternative approaches on that issue. And then finally, how are we going to get there? I want to share a little bit about the opportunities with performance-based rules and what they're allowing for innovation. So just to kind of do an overview of advanced air mobility, I'll use Uber's generic aircraft. Mike did such a good job showing aircraft. I'm not going to belabor this too much, but I think you can see that you're basically looking at an airplane. A lot of airplane features in this, and that's true for a good chunk of the new designs, if they're not strictly multi-rotor. The other thing you see is it has vertical lift capability. So you're now, if we're talking crashworthiness, having to look at forward airplane type considerations as well as vertical like helicopter considerations. There is a little bit more to look at with this, and that is size and passenger carrying. These typically are 1, 2 to maybe 6 passenger aircraft. That's where this is going. You see that clearly with this. I included a conventional airplane because it's part of this new generation of aircraft, and it's with battery and electric, there's a chance to really build in some safety. So moving on, let's talk a little bit about the certification cost and how it doesn't really align well with the safety benefits when we're talking about the traditional dynamic seat approach, and the need for thinking a little bit broader and more innovative and looking at alternative approaches if we really want to improve occupant safety, which we do. And if you look in the background, this accident kind of sums up one of the big problems with small aircraft, in that they just don't have the consistency in terms of accidents that we see in larger aircraft. The NASA testing is wonderful, but it doesn't capture all the problems, and I'll talk about that in a little bit. I think that there is some weight, inertia, break point where below it, and we could say 4,000 pounds, just kind of as something to wrap your head around. But when we talk about accident scenarios, you look at biz jets, transports, helicopters, they tend to be fairly consistent. As you get smaller, especially with single engine vehicles, you don't see the consistency in the accident scenarios. And the reason that's important for these, when we talk low weight inertia, light wing loadings, light disc loadings, the very specific dynamic testing scenarios don't line up with the accident service history. I would project that the eVTOL aircraft may have the same variation in accidents, maybe a little less in terms of, because they have, or they're going to have more redundancy with the propulsion systems, which is excellent, but they may be operating over more challenging environments and more challenging weather conditions. So one of the reasons that I bring up dynamic seats is because it's the most expensive component in a small airplane today, next to the engine and avionics. Years ago, when I was at Mooney, that seat and passing the test cost more than an entire STC for a new engine, new gross weight, expanded fuel tanks, new instrument panel, better performance. I mean, it was a substantial STC, and the seat cost more than the rest of the whole entire STC. It's something that we really have to have a conversation about. As I said, they don't align well with the cost of showing compliance, but that doesn't mean it's wrong. I mean, this is the right idea. We definitely need energy absorbing seats. As Mike brought out with the landing gear, there are other things you can use on the aircraft for energy absorption. The real question here is, what's the level of precision that we're putting into the requirements, okay? And does that really provide the associated safety value? Is there a place where we can get a better balance? I would offer that more emphasis on maintaining survivable space for occupants is critical. You see that isn't there in a lot of the older airplanes, and with a lot of the accident scenarios we see with older airplanes. And I would offer that this is already an ongoing project in ASTM 44 for airplanes, and I'm fairly excited about that because they're leveraging the ability for these alternatives, and it's something we want to apply to the VTOL aircraft. So just going into a little detail here, when the bulk of the cost for safety goes into a seat, it's like putting all your eggs in one basket. And that's okay if that works in 90% of the cases, or even 80% of the cases. The trouble is with these small aircraft, there are all kinds of variables. So for the dynamic seat to do its job and be the bulk of the safety in a small aircraft, I'm going to have to be able to get into an open landing area, and I'm going to have to land or impact the ground exactly like the test. A little bit tough. We keep trying to train pilots how to crash. They just don't listen. It's a frustrating situation. I joke. The other thing is, if you're not 170 pounds, the seats don't work like they're tested. And then one that I think is often overlooked, occupants have to wear their seat belts correctly, and that isn't always the case. So before we move on, I would just like to point out that whole thing about putting all your eggs in one basket. If that is a very expensive test, it kind of drives our manufacturers to where they're going to be reluctant to look at doing additional safety things for no credit, because that's extra cost and weight. So we have to figure out how to spread that out. And I would offer that now with performance-based rules, I think we have the ability now to easily adapt some innovative approaches. So those of you familiar with the dynamic seat rule recognize this. It's almost a book in the old rules. You take the CFR book, it was roughly 2.5 pages, I think, in the old small book. So this is not only extremely prescriptive on what the seat has to do, but also how you have to test it. So it goes beyond a typical rule, very, very precise, and that drives cost. So when I talk about performance-based rules, that's kind of a top-level flexibility that's allowed in 2364. These are the new emergency conditions, as we call them. And you'll notice that this doesn't tell you how to design and test the seat. what it does is it defines the intended safety outcome. And that's the intent. And now maybe you can get to this intended safety outcome in a lot of different ways, probably leveraging off the dynamic seat concept, but maybe now you're allowed to get credit for doing some other things that could really enhance occupant protection. So what's that available on? Obviously CS23 and Part 23, but I would also offer that EASA's eVTOL, which leveraged CS23, has the same language and leverages that. I think they bias it towards Part 27. The FAA is taking the same path for these vehicles with Part 23, and I think they're using very similar language, if not the same language. And I know you've seen the Swiss cheese diagram a lot, but that's really what we're talking about here. Historically, we've had primarily one slice of Swiss cheese. And as long as all the holes in that one slice line up to the accident scenario, it works great. It's outstanding. The trouble is they don't line up. And so what I'm proposing and what I'm kind of trying to plant the seeds for is the need to maybe add some layers of Swiss cheese there in other areas like airbags, survivable space, things that will help when the accident doesn't line up with the traditional tests like you saw with the NASA pictures. Fortunately, we're not locked in to those prescriptive requirements anymore, but applicants are going to have to propose this. I'm hoping that the authorities will work with our industry and kind of come up with some credit for doing different things, maybe look at modeling, more credit for modeling, and a mix of tests and that. So the historic approach to safety with all the different parts, 23, 5, 27, 29, is to prevent the accident. And that is the best approach in aviation, and that needs to be our focus. I'm pleased to tell you that virtually every manufacturer out there is leveraging electric and some of the cool features to put redundancy in, flyaway capability. The advancements in flight controls are going to address a number of the target areas that have caused accidents in the past. So I think you're going to see a major reduction in accidents in terms of the sophistication and safety we can get with electric and modern flight controls. That said, as Justin showed you in the first set of slides, the numbers of aircraft and the numbers of operations we're talking about pretty much ensure that we're going to have accidents. There's just no way around it. History says it'll happen. So how do we do that? How are we going to address that and keep the public interested for this urban air market that we're really excited about? And I would offer that maybe we need to start thinking more about how this looks from an automotive standpoint. And by that, I mean accounting for the fact that accident scenarios will have a lot of variation, right? I've already talked about that. Since it's unrealistic to count on just preventing the accident, what we need to do is accept and expect that we will have some. And then in the blue, as I really want to highlight, we need to start thinking about this more from the automotive industry, where the goal is to protect the occupant and allow them to walk away from accidents. You know, people aren't afraid of driving at all anymore because there's so many accidents that might have been fatal a decade or two ago where people just shake it off and walk away. Furthermore, you look at what folks like Simpson Racing have done for Formula One and NASCAR, and the accidents that the drivers are walking away from. It's just phenomenal, the technology that's out there today that for occupant protection. And that type of technology, while we recognize there's weight issues, and in F1 obviously there are just what they wear, and there are other issues with racing that aren't practical for us. I think some of the technology and concepts are things that we can use. But while we're talking about that, talking about all the safety benefits, there are other things that we need innovation for that we're going to have to leverage these alternatives. And that is that when we're talking about electric vehicles, the weight sensitivity is extremely high, meaning for every pound you add, you may have to add 7 pounds or 8 pounds of airframe. It is a big deal on any aircraft, right? Weight. But I think it's a bigger deal with electric. And so we have to be sensitive about that. Just from a practical standpoint, one of the ways to address that is to try to build this stuff in the initial design phase. And with that comes early discussion with the authorities so that our manufacturers know they're going to get credit. We have to all be on the same page when we're going down the path, right? The second one is when you're doing something innovative, right, it needs to balance out with that safety value. And when I talk about it, I want to just share a few things with you from a practical consideration, right? We're talking about moving a lot of people through fast because the target is urban air, like an air taxi. That's probably where we're going to see most of this. The advanced air mobility, I'm excited about for some of the long runs, but the short hops will happen fast. Well, one of the aircraft I fly is acrobatic, and because of that, I have a harness like this, and I'm going to tell you, it's an awesome harness, and I feel like if I hit the ground and the steel roll cage hold, that harness is going to keep me alive, and I'm not going anywhere. The trouble is, right, I have to plan about 5 minutes to get into that damn thing. Moreover, if I take anybody flying in it, I literally have to do the seatbelt for them because it's too complex. The other aircraft I fly has a traditional car seatbelt, okay, with an inflatable restraint or an airbag. Now this one is awesome in the sense that people can get in, they know how to do it, it's very easy. They're very comfortable with it, they're used to it. The downside is it may not give you the protection you need in a weird accident. There's nothing to keep you from submarining under that, for example. And now for a little bit of technical humor. In the US, we have an amusement park in Ohio called Cedar Point. It's one of the best roller coaster parks in the country. I love going there. While I'm standing in line and watching these people who don't know anything about the ride, don't have any experience technically, get on, pull that thing down, and go upside down, and then they're off. They're moving people through so fast. I wanted to show it just because when we talk about innovation and maybe brainstorming, I mean, I'm not nuts. That's too damn heavy, too cumbersome. Nobody dressed in business clothes is ever going to do that. That said, maybe there are other places we could look for ideas besides automotive and racing that will give us more safety, more occupant protection in the event of an accident. So going forward, I think it's important, it was something Joseph said, that crashworthiness needs to be in the primary design. It needs to be a consideration in the beginning, not something you add to later, not just for weight, but for planning. And instead of our current fixation on the seat, we need multiple features like the Swiss cheese approach. We need a system for occupant safety. The seat's important. The stroking, energy absorbing aspects of the seat and the airframe are very important, but they're also important from other angles. And there are other things like the airbags that could actually benefit from unexpected accident scenarios. Also, and this is critical going in, we've got to consider the cost. If we're going to promote multiple features, we're going to have to consider cost versus safety benefit to get the overall system working. And then finally, where this really comes into play when we talk cost benefit is the level of precision of the test. The dynamic seat testing may actually be more affordable today. When we were doing it before, it was trial and error. So we had a trial and error approach to get a decimal point type accuracy, and it just made it crazy expensive. Did we really need that level of precision? That's the question that we need to be asking. What's an adequate level of precision? 1%, maybe 20%, 20% with 5 other features? I don't know. That's the kind of thing you need to ask as we go into this and consider, because risk allowances drive cost. Cost is its own thing. And then the safety continuum is a piece here too. How many people are going to be on board? How's it going to be operated? I heard somewhere where a number of these are going to be used as crop dusters, and well, in the safety continuum concept, maybe that's a different place in terms of crashworthiness. So that's all I have, Justin. I'll turn it back to you.
Thanks, Lowell. Yeah, great presentation here. There are a handful of questions on the Conference.io app, and I'm gonna go through a few of them. The first, and I think you've touched on it already, but one of them is, what do you think are the most important features for eVTOL companies to incorporate in their aircraft? And the sense that I was getting that from your presentation is all of them, but I'll let you I'll let you comment further.
So I think that when you say all of them, you're pretty close. Most likely, you're going to see more vertical impacts. So I don't want to discount the energy absorbing seat, but I really can envision other type of impacts where you may hit something. And that's what we see today, right? Rollovers, side impacts. That's where you may be able to leverage airbags. I know if I ball up my car, the whole thing becomes a cocoon of airbags. Now that's probably, from a weight standpoint, impractical, but maybe there's something a little milder that you could consider. Better harness system, something that people are willing to put on. I mean, those 3 things are going to get a lot, 90%. There are a few other features from the racing car industry you might look at. Well, and crashable roll cage. Keep the space, please. Sorry, I should have said that first. That's critical.
No, that's all right. That's interesting because there's there's 2 questions really that talk about automotive crashworthiness, and especially like the IHS or NCAP kind of criteria, and these are more comments, so I'm not going to directly ask you these questions, but these are good comments, and we will save them and address them at a future time, since there's 3 of them that are very close. The final question I'll ask you today, it's what do you see, since you're talking about the dynamic seat testing, what do you see as a difference between a dynamic seat test for an eVTOL versus a conventional Part 27, or is there one?
So I think that's actually currently being discussed. I don't know if it'll be somewhere in between. You might actually make the case where you need to account for both the forward for airplane and the vertical for helicopter. And so one of the points that I was trying to make is maybe we do that. That's okay. You probably do need to account for the test criteria, but maybe you could do it in another way from a test, i.e. some computer modeling. Maybe you test components, get confidence in the computer modeling. I know that's going on today already. Maybe it could be expanded such that you're giving credit in terms of that flexibility. Instead of 1%, maybe 20%. You're in terms of uncertainty. You're giving credit for that while you're still trying to accommodate the levels for both airplane and helicopter. And there's multiple ways to hit it. It's not just something you ignore. Okay, and I'll do one final question here. I wrote this question down. It might be a question for Bob, but I like it. And I just want to hear if in your talks with the FAA, do you have any kind of estimated timeline as to when any kind of means of compliance documents will be developed or certified? I don't. I know the effort's going on now in ASTM, and I assume that question was for eVTOL. Yes. It's just kicking off, so it's down the road. Bob may have a better feel for it than I do. And maybe that question gets asked again when Bob's presenting. Well, or Eric's. Eric. Yeah. Correct. Yep. Good one to ask. Yep. All right. Well, thanks, Lowell. Appreciate the presentation. It's good stuff. I'm going to turn it back over to Joseph for our next speaker. Thanks, Justin.
Oh, thank you, Lowell. Our next speaker will be Ryan DeRue from Uber, and he's going to give a talk on the operational expectations for eVTOL aircraft. So he's going to talk a little bit about the operational modes and how the expected usage. Ryan DeRue is a regulatory affairs specialist at Uber Elevate, where he is responsible for regulatory interpretation and strategic advocacy on topics including eVTOL airworthiness, UAM infrastructure design, operational requirements, and flight crew licensure. Ryan studied aerospace engineering at Georgia Tech and economics at Binghamton University. Over to you, Ryan.
Ryan, you are muted.
Ryan, you're muted. And Chris, can you clear the questions, please?
Thank you. Sorry for that. Appreciate the patience here as we brought up the microphone. Hi, I'm Ryan DeRue. Pleasure to be with you today. I'm the regulatory affairs specialist with the Uber Elevate project, and really important topic today, which is operational expectations for eVTOL aircraft, particularly on the Uber Elevate network. We're hoping today to inform our crashworthiness experts so that way they can better address the issues ahead of us. And I think that the most important thing, especially coming out of these first few presentations that we're going to talk about today, is that we can perhaps contextualize a little bit, focus in a little bit finer on some specific aircraft, some specific operational scenarios, such that our crashworthiness experts can really hone in what we need for these vehicles. So I'm going to go to what is Uber Elevate? So Uber Air will be an on-demand aerial ride-sharing service. So on-demand means that a ride request can be made in real time without prior booking. The Uber Air concept and technology that enables this on-demand service will be leveraged from Uber's ground mobility services. And the term aerial ride sharing means that each Uber Air ride will be shared or pooled at the origin of the flight leg. There's 5 major steps to a multimodal aerial ride sharing experience. We have the first mile. So this will be either in UberX, perhaps a new mobility solution like a shared bicycle or scooter, origin skyport operation, the flight segment, the destination skyport operation, and then the last mile. You're seeing these segments displayed for you on the screen. As you may know, our rider analytics and simulation tools really provide Uber Elevate a unique ability to provide deep insight into how people move throughout cities. And as a result, we're able to set appropriate vehicle requirements for vehicles operating on our network. As you see on your screen, this means that we need an aircraft that can fly at 150 miles an hour, that has 4 passengers and 1 pilot in terms of payload, as well as their associated baggage. A range of 60 miles at least at maximum range, but a typical mission may be around 25 miles. They need to be quiet, at least 15 decibels below stage 3 limits for existing aircraft. And they need to be electric. We really believe that, in terms of zero emission and minimum infrastructure requirements, we really don't want to be managing fuel. We really think that all electric eVTOL aircraft are the right solution for this mission. We think that these aircraft are going to fly a lot, and they need to be reliable, and they need to be able to complete somewhere around 2,000 flight hours a year. Today, Uber has 8 OEM partners developing eVTOL aircraft for our aerial ride-sharing mission. All aircraft that meet our operational specifications, you may note, have a wing, and will, throughout most of their operational flight time, be under wing-borne lift, like a GA aircraft. In many ways, it's often more appropriate to consider these normal category airplanes with a VTOL capability. As Joby recently described their aircraft in Aviation Week, it's more akin to a high-efficiency glider in cruise. Wing-borne features and crashworthiness are somewhat well understood and well documented in agate studies, NASA and FAA technical reports. So today I really want to contextualize the VTOL takeoff and landing environment, which perhaps is going to be unique for these vehicles. When we talk about crashworthiness, like I said, it's going to be critical to contextualize the vehicle and its expected operational environment. Uber is in a unique position to help inform infrastructure design standards and other aspects of the system necessary to support these new technologies through our ongoing collaborative research and development work with our OEM partners, FAA, NASA, and others. With infrastructure, we anticipate that the existing airport and heliport design standards may be adequate for many eVTOL operations, supplemented as appropriate with engineering briefs or other interim guidance to support modifications for supporting systems necessary for battery charging, stationary energy storage, and fire protection. We definitely believe that it's a critical time for regulators responsible for infrastructure standards to closely interface with certification projects to best capture and utilize relevant flight test data. And I think that this has impacts for crashworthiness as well. I'd now like to pivot to some thoughts about typical rotorcraft performance and flight profiles into and out of heliport facilities. And then I'll discuss why eVTOL aircraft, particularly the ones designed to Uber specifications, should potentially be thought about in a more specific way, and what we should expect from the approach and departure from these aircraft. Okay, so let's go into ordinary rotorcraft right now. We have here the height speed envelope as required by 2787. The height speed envelope is normally referred to as an HV diagram as well. It defines the envelope of airspeed and height above the ground from which a safe power off or one engine inoperative landing cannot be made. The diagram normally consists of 3 portions. So we have the cruise portion, the takeoff portion, and the high speed portion, all of which are indicated on that diagram. The high speed portion is sometimes omitted on occasions when it's shown that the rotorcraft can suffer engine failure at low altitude and high speed and make successful landings or climbs on the remaining engines. The same is true for the takeoff portion, but we'll get to that in a minute. The avoid areas of the HV diagram are separated by the takeoff corridor. This corridor should be wide enough to permit a takeoff flight path clear of the HV diagram using normal pilot skill. The takeoff corridor should always permit a minimum of plus or minus 5 knots clearance from those critical portions of these limiting envelopes. And although helicopters are not restricted from conducting maneuvers that will place them in the shaded area of the HV diagram, it's important for pilots to understand the operation in those shaded areas expose the pilot, aircraft, and passengers to certain hazards should there be some sort of engine or propulsion malfunction. The pilot should always evaluate the risk of operating maneuvers in these areas. I wanted to address an earlier question about auto rotation requirements. I think it's really important to understand that the 2775 requirements don't specifically require auto rotation for all VTOL aircraft. For single engine rotorcraft, it needs to be demonstrated that they can enter steady state auto rotation. But for multi-engine rotorcraft, what you need to be able to do is show that the approach path will allow for smooth transition to one engine inoperative landing flight. And I think that this is really going to be important to remember as we think about vehicles that have lots of distributed propulsion, and what one engine out might mean for them is perhaps very different from what one engine out might mean for a multi-engine rotorcraft. In particular, when it comes to the all engine out landing and requirements for auto rotation in 2775, really what we're getting at here is that we have to say that it's possible to make a safe landing. And this is from the Part 27 means of compliance. It has to be possible to make a safe landing after complete power failure from normal cruise. And so when you think about a winged eVTOL, normal cruise isn't going to be in a powered lift mode. It's going to be in wingborne lift. We're going to be gliding in that situation. It's very unlikely with these vehicles and their redundancy that we'll ever encounter even a full engine out, full power out situation in normal cruise. But just really wanting to be specific, the ability to auto rotate is a means to demonstrate compatibility with a safety objective, which is the reasonable assurance that descent can be arrested and forward speed controlled to allow for a safe landing with no injury to occupants. So just wanted to hone in really quick on the auto rotation question. I think it's really important that, it's not being able to auto rotate does not disqualify an aircraft. It's whether or not it can meet the safety objectives of continued safe flight under one engine inoperative or, arrested landing. Getting more specific, particularly to certain Part 27 and many Part 29 rotorcraft, we understand Category A performance requirements, and really, in short, this assures that there's adequate designated surface area and performance capability for continued safe flight or a safe rejected takeoff. And Category A performance, imparts requirements both on the vehicle design but also on vehicle operation. So, for example, what you see on the screen here is a takeoff profile for Category A rotorcraft. And the helicopter here is brought to a hover and ground effect and then accelerated with translational lift. Now, it's important, again, that we understand that this translational lift is related to that takeoff corridor, that limiting envelope, that HV envelope, as I was discussing in the previous slides. For expediency here, I'm going to kind of skip forward. But operationally, this vehicle is flown in a way that if there is a single engine inoperative, it's either able to continue safe flight or land in a particular way. There's other types of Category A takeoffs as well. The left diagram being from a ground heliport, the right from a pinnacle heliport, perhaps from a building. Here you can see that minimum takeoff distance of 0 feet can be achieved through the use of a vertical takeoff. And the following figures show those two representations. I mean, it's really important in this procedure that a safe landing is possible from any point in the procedure up to that CDP, which is the critical decision point. It's that node just after the vertical climb. So what typically happens is, in order to enable this kind of departure, we sometimes take weight penalties in terms of our total max payload on takeoff in order to allow that HV diagram to collapse and allow for that vertical takeoff. Now, this is not necessarily the greatest situation, and with vehicles like eVTOL that are quite payload constrained, we have to be thinking, well, what's the optimal departure? Can these vehicles operate safely? And I think that the answer really is yes. So just to hone in on aircraft with limiting HV envelopes, we have horizontal flight profiles similar to the one I showed in the first diagram, and vertical flight profiles in the second two diagrams. Okay, back to eVTOL. So a hallmark of eVTOL technology is redundant distributed electric propulsion. We see that some aircraft meeting the Uber Elevate specifications can can sustain continued safe flight after the complete failure of a single propulsion element, and that the need to develop translational lift is no longer a typical requirement for a safe departure. It should also be reiterated that these vehicles are expected to spend very small amounts of time in hover, both for power and acoustic reasons. These are not helicopters, and they are not designed for long duration hovers or low speed operations close to the ground. They're meant to lift off, depart, fly and cruise, and get to their destination. So what might this mean? Well, if you look at the modified HV envelope, as you see on the left, you can essentially do that departure or a direct descent departure. We see that some rotorcraft are capable of doing that today. The AS355, for example, as you can see, has two different types of departures listed in their AFM. They can do the vertical departure if they take that weight penalty. Otherwise, they can do some type of translational lift departure. Now, what I really want to get back to with distributed electric propulsion is that the single element loss of a propulsion unit is not going to be as critical as, for example, let's say a twin engine rotorcraft, which may now have lost up to half of its available power. And so, we really do expect that the vehicles that are going to be operating on our network will likely be able to fly more direct flight profiles and quickly get onto the wing and fly and cruise. I have some concluding thoughts. eVTOL are in the certification pipeline today. Their certification bases are very well along. I think it's really important that, as first movers are paving the way for future efforts, that industry work to help that these first movers find their success. Their success is going to be our success. And so I think events like this are very important, such that we really set a strong foundation for this industry. I think there's a few interesting concepts I'd like this community to consider, specifically with respect to unique capabilities and considerations for eVTOL. The first is perhaps to consider optimal trajectories for crashworthiness. And in this case, I mean both in terms of speed and climb angle, such that there's an optimal flight path for emergencies. I think that we are in a really unique stage with very, very capable vehicles, and we can start thinking about optimizing for other types of points when it comes to these departures and arrivals, and crashworthiness may be one of them. And again, going back to that, so it's not just speed and climb angle, but perhaps the optional flight path over particular areas. Maybe it's beneficial to fly over a highway instead of buildings on initial climb, things like that. I think it would be interesting to understand sort of the implications of that. The second is with respect to automation. So automation will, in large part, fly these aircraft. They will adjust their deck angles, not the pilot. The pilot's going to be requesting a rate of direction of movement from these aircraft, up, down, left, right, and how fast. The aircraft will respond as appropriate to deliver that request. So if we think about that in respect to crashworthiness, the question then becomes, how will the automation fly the airplane into a crash situation? And I think that this is a really interesting thing for crashworthiness experts, perhaps that we've never dealt with before, in that the computer can perhaps, when it realizes it's in a critical failure state, align the vehicle for ideal impact, orientation, velocity, etc. Requiring the pilot to do that sort of maneuver is perhaps not necessarily the way of the future. I think that this is an area with rich opportunities for research, and I'm encouraged by the excitement that's in this crashworthiness community to take these types of hard questions on. And a last thought, as we talk about seatbelts, I would really be interested in understanding more about automatic seatbelt tensioners, which are not common right now in aircraft. The question is, can we reduce the weight of that equipment such that it's not such a burden to incorporate them on board? And with that, I want to thank you very much for listening to the presentation.
Oh, thank you, Ryan. I got a question. I know you probably addressed some of this in your talk, but assuming the operations that you have, do you see any limiting factors from crashworthiness that would maybe affect how you might operate or fly, or what types of vehicles you guys would be looking at?
Well, I think that it's really important to reiterate that any vehicle operating on the Uber Elevate network will be a certified aircraft. And so, with respect to crashworthiness, they will meet all requirements as, required by CAAs and meet those needs. So, we wouldn't compromise on safety there. We're definitely going to take certified aircraft. In terms of, are we going to operate in a specific way with respect to crashworthiness? I think that, again, there is a lot of opportunities with respect to automation and how we can, ideally fly these aircraft such that they encounter a crash situation in the best possible way. I know that this is a very new concept, and so I'm really excited for where research could go with that.
Thank you. I guess we have no further questions at this time. And actually, we are actually oh, wait. I guess someone just put in a question here. It's on autonomy. It says, in the future, how do you derive sufficient confidence in the autonomous capability to no longer need crash mitigation structures? And also pulling the same thing from the autonomous, when you look at the self-driving crash avoidance features you see in the self-driving vehicles, how do you see that maybe being applied to these vehicles such that you're kind of, bringing that capability in so you're confident with it?
Yeah, I think that, let me qualify my response here. I don't think that in any way will we be suggesting that automation can replace crashworthiness structures and technologies, stroking seats, crushable impact areas, survivable volume. Those are all always going to be important. I think that what I'm proposing with respect to thinking about automation and how that impacts crashworthiness, how can we achieve a higher level of safety? How can we make more crashes survivable? How can we provide the best possible occupant outcomes? So really, really excited for that. Not proposing that we replace or get rid of anything. It's sort of how can we reach the next level? And I think that with respect to eVTOL and automated flight computers and mechanisms, we can think about new ways to pull different levers.
Right. Thank you. Good description there. Like I said, and with that, we are ready to take a short break. Christine will put up a quick counter, and we will be back in about 15 minutes, and then kick off our next three speakers at that time. So thank you. Just hang on. Everyone take their quick bio break and come back and see you in a few minutes. Okay. Welcome back, everyone. So hopefully you all appreciated our short break. I know sometimes we sit in these long virtual meetings and we just long to get up and move around and stretch out for a minute. We have 3 more presentations before we conclude. And our next one up is by Bob Stegman from the FAA. And he's going to discuss eVTOL crashworthiness and moving forward. Bob is an aircraft structures engineer with the FAA Small Airplane Standards Branch. It's over 30 years in aviation work, 11 in airline maintenance engineering, and 14 with the FAA. Much of his work at the FAA is focused on composites, crashworthiness, airbags, ballistic parachutes, accident investigation, and first responder training. So I will turn it over to Bob at this time.
All right. Hello, Joseph. Thank you. My name's Bob Stegman. I'm Small Airplane Standard staff. We're going to go through some of our. Is it working for you? Okay, there we go. Okay. Start with the certification on eVTOLs, safety continuum. You've probably seen this kind of an eye chart slide here, but it is it's really a range of certitude based upon acceptable level of risks. Obviously, we start at the bottom with UAS. They have very little requirement for public safety, or not requirement for public safety, but public risk. Public acceptance of risk is high, so their certitude is rather low. Whereas on the other end of the spectrum, you have 25, where transport category passenger airplanes have very high level of public safety, and obviously we're all familiar with this this continuum. But instead of a line here, we wind up with not really necessarily a line is when it comes to certitude, but more of an error cloud above and below that. Whereas it's primarily tied to occupancy, but now we're starting to look at protecting people on the ground, which adds a little bit of fattens up our error cloud there a little bit. And in some cases, like UAS, may have higher expectations if they're flying over large crowds, for example. So when we keep this in mind, we're looking at aircraft safety and and how that fits into our level of certitude. I.e., the point is that when operation or our utilization model changes, our level of safety may change too. So what we want to do, and we've mentioned it several times today, is we want to tie this safety, this crashworthiness, deeply into the aircraft, into the design, and so it's adequate to accommodate change. It's unlike has been mentioned earlier before. We're not going to just we hope not to think of crashworthiness as a last thought, and is something we want to throw in as a crashworthy seat. Just throw in a seat and call it good. Pass our dynamic seat test. Fail our dynamic seat test on a Wednesday. Pass it on a Thursday. And never look back. So kind of changed a little the way we've thought about crashworthiness. So looking at our aircraft configuration, we need to, as we start our cert steps, we're going to look at the configuration, look at the utilization. Is it more of a 23 or 27? Obviously, we're going to use that term as a fixed wing airplane or a rotorcraft. And obviously, as we've discussed earlier, again, eVTOL just don't seem to fit into the normal certification holes, and so we're seeing that as we see a lot of these airplanes vehicles start to come in for try to start to apply for certification, and we have a real challenge, obviously, trying to plug in the right requirements with the wide variation of designs. They are definitely, no doubt, deviating from the traditional 23 and 27. Nothing new there. So obviously now we're proceeding with the known. We're throwing 23 and 27 static and dynamic crashworthiness at them. That is typically where, we're kind of considering how the vehicle flies and lands in an emergency. That's what they're based upon. We may move towards some sort of Part 27 7 fuel tank requirements, like a 50-foot drop test maybe. Thinking batteries here, this is nothing in stone yet. It's actually dealt with more in the power plant side, but with the congressional mandate on rotorcraft, it probably seems reasonable that we consider how these vehicles do, batteries do with the power or the batteries, I should say, as far as how they deal with impacts, so they're not a post-crash fire hazard. Again, we are incorporating crashworthiness best practices in the survivable volume. Obviously, these crashworthiness practices come out of a lot of the new Part 23 rewrite Amendment 64, where we are looking or giving a little more credit for looking at holistic crashworthiness, if you will. Whereas survivable volume, looking at occupant restraint, the interior protection, how the occupant's going to do inside the airframe or the aircraft. Obviously, airframe load attenuation, looking at anti-plowing features, try and ride the airplane out of the crater, slow down slowly. Post-crash fire protection and good egress. We've come across those best practices. We've talked about them earlier today, and they're still something we're really pushing on the newer vehicles. What we're doing now is given obviously I deal with fixed wing airplanes, and we're seeing our organization sees we take on a little more responsibility for the fixed wing airplanes or fixed wing aircraft with wingborne lift. And what we're seeing now, what we're actually applying now, we're using the known, and we're applying amendment or 23, 561, 562, the crashworthiness, and the 27. We're combining kind of the worst of both worlds, and if it has a vertical takeoff component, it's going to get vertical. If it can fly forward on a wing, it's going to be able to. It's going to be looking at some horizontal worst case scenarios. So, end of the day, what you have is the worst of each highlighted here in this chart. And on the right side, you can see the actually what has been applied to some of the early applicants. It's what we know. It's what we're comfortable with. We don't have a large amount of data to use otherwise. So we're proceeding with the known. Likewise, we're doing the same thing with dynamic seats. You can see the same chart here where we're looking at the worst case Part 27 vertical impact dynamic seat tests and the forward impact of the fixed wing or the Part 23 fixed or Part 23 dynamic seat test loads. And again, on the right side, you can see what an applicant will typically tend to see. So to this point, this is where we are right now with current applicants and our adapted requirements. We've adapted them to eVTOL. But from this point on, this presentation really mixes the known and kind of suggests a plan forward into a better predicted solution for eVTOL crashworthiness, because they are so unique. Each one has its own characteristics. So this is not FAA policy. It's not data that is directly suitable for certification, but these are things that need to be discussed in the future as we start bringing these airplanes online. So we really need to start with an emergency landing. What is an emergency landing? We bound an emergency landing for Part 23 and 27. It's an impact where the aircraft is under control at impact or at least just before impact. So we're looking at maybe stalling an airplane as you bring it into the ground with a fixed wing, or with rotorcraft. We're looking at, it's really defined by how we can control that impact. If your aircraft's out of control, really all bets are off. So in this external condition, we're going to look at crashworthiness, and we really draw a line in the sand based on human tolerance for really two conditions, either a aircraft landing or a fixed wing 23 crash landing, or a 27 auto rotate. And really we draw a broad line in sand for pretty much all of those types of aircraft, and then we build our crashworthiness off of that. But with eVTOL, we're kind of in a little bigger, got a lot more variability based upon the aircraft's operation. So we see this. This is another eye chart. You can see these charts. There's multiple charts of this. This data is collections of accident data over many years, and they'll define a survivable impact, or they'll determine what is considered survivable, and then we'll build our crashworthiness off of those. That's where dynamic seat testing originated in charts like this and studies like this from Agate and some of the NTSB data, and Army's done the same thing. So you see these types of charts on the right, but you got to look back in 23 and 27 emergency landings. They're based upon years and years of data that we simply don't have for eVTOLs. And again, eVTOLs will offer a lot more variables, and we don't have this crash history with them. So picking a definable survivable point on a curve is a little more of a challenge. So like Lowell had discussed earlier, we'd kind of like a vehicle that could obviously be able to handle a lot more spots on this, and not just picking 2 points on a surface of possibilities of impacts. We'd like to have a vehicle that can handle a lot of different cases, and general is probably better than fine-tuning your vehicle to one occupant weight and a couple of different orientations. So obviously what we really need to look at is we need to marry, we need to define really, we need another way down. We need to define a controlled emergency landing for these eVTOLs. That's going to help us target our crashworthiness. It's really the basis for crashworthiness, that we use assumptions that we, in part 23 and 27, that we really is really a little more of a challenge to use on eVTOLs. So obviously we need to define control our emergency landing. We need to be in control, and we need, and it's pretty good assumption that it's not going to look like a 23 or 27 emergency landing. So the elephant in the room is 23 aircraft. They assume some wing lift to an emergency landing. 27 can auto rotate to an emergency landing. Yeah, we have typically with these eVTOLs, we're going to see a lot more rotors. You'll probably have a lot more residual lift, but you really have to think through the entire failure sequence to the ground, so we can hand it off for crashworthiness, so we can really bound our problem. Obviously, auto rotate's really not a thing in nearly all of the things we have. They're typically fixed pitch thrusters on these eVTOLs, and auto rotate's just not a thing for them. So you really got to say, you got to tell us what you bring to the table as far as bringing a vehicle down is to bound a crashworthiness situation. So we don't have much reason to believe that emergency landings, they're not going to be like 23 and 27. So again, another way down to controlled emergency landing. And it's not that you have to come up with a new one. You just have to use the ability your vehicle has, and your vehicles, they vary so much that it's going to marry system safety into crashworthiness like we really never have before. Your failure scenarios all the way to the ground. So I know Ryan went through a lot of this. He's thought through a lot of this. Kind of a good example is what your vehicle can do, what kind of places you need to stay out of, how you can bring the aircraft down, and what your scenarios are, really to think through these emergency landing parameters. So obviously we need to define what kind of direction and magnitude of the way a vehicle can come down, so that crashworthiness can really have a fighting chance to do its job. If it's way off the charts and way outside those curves, we can pick something, but we don't really know how applicable it is. It's it just operates on a different paradigm. So really, what system you need to figure out, what system redundancy or features are available to your eVTOL in an emergency landing. If it's failed, what can you use? Not saying it's not possible. It's just that eVTOLs need to use the strengths they have and define what kind of crash you would expect to have. and it's again, it's going to be unique by the aircraft, and we do have some specific concerns, as Ryan had mentioned earlier, about transition flight and low speed, low airspeed, low altitude, coffin corners of the envelope. Those are dangerous spots, and again, operation over congested areas just makes it a little more of a challenge as to how you're going to bring an aircraft down. So in all these scenarios that should be considered, really need to consider the response time and the recovery time, and how does automation play into that? It may be automation may drastically help. I mean, it's probably way better than human response time to some of your potential failures. So it's not that it can't be done. It's that you need to determine what your vehicle brings to the table, what features it has. You may have a situation where you have a vehicle that has wing-borne lift, and you can lose an engine or maybe two engines and two motors, and you can still bring it down for super slow stall speeds to landing. So that's good. That's goodness. And I mean, maybe you could even bring it into stall speeds such that they're so slow you could start using some of our slower stall speed landing or crashworthiness requirements we're using right now for part 23, like low stall speed aircraft, like aircraft below 5 knot stall speed. That's something we could probably talk about if you determine that your aircraft can fly really slow and bring it down easily. So it really is incumbent upon the applicant to demonstrate the aircraft's ability to deliver the aircraft to emergency landing conditions that we can use our crashworthiness on. Really, what we're really after here. So obviously, how can we control descent? We have residual thrust for multiple rotors, residual thrust coupled with residual lift. These are all things that you've given thought to in your failures, but we're going to be looking at how a failure hazard assessment really can help us here. We're going to take things that can go wrong and really take them all the way to the ground in scenario. That's what we kind of like to see here to define that emergency landing. So some of the fixed wing aircraft that we've seen, obviously they're optimized for a different kind of flight, typically maybe a higher speed flight. They're not necessarily given flaps for a slow speed landing. So control redundancy is a part of that failure hazard analysis that we can't really you need to put flight controls in if you're not going to put or show redundancy for flight controls. Some use differential thrust, differential torque. All of that plays into the functional hazard assessment because just controlling our emergency landing. And again, as mentioned before, how is automation going to affect our emergency landing? Finally, I want to mention here, really on this point, is ballistic parachute systems. Remember that they do have limitations. We've had a lot of applicants come and discuss the idea early on, and we really, as the FAA, this has traditionally been a supplemental safety system, and it's really not. It's just a new way forward for us. It'll be a little slower way forward for us, maybe, because it's not really ever been used as a primary safety system. So remember that as you use it, you're really trading a controllable situation for an uncontrolled situation. You cede control, and it may have a better outcome. And remember also that the established performance for these ballistic parachute systems is is based upon a lot of airplanes that have come down undershoot, but remember, those airplanes burn fuel. They burn a significant amount of their weight, so they're landing a lot lighter, a lot easier than electric vehicles that are going to come down full weight every time, or nearly full weight. So it's going to be a little different results. I think the body of data will probably be a lot more sporty in landing with heavier vehicles every time. And then again, limited envelope, they're not going to be useful at low AGL. It's not an easy button. It's something that definitely has a limited envelope. It's not going to be used at low AGL. Even at higher altitude airports, you're going to hit a lot harder. Those are usually taken into account, but those are limitations. Even if you come down in the mountains, how hard are you going to hit? And again, it would become a minimum equipment list item. And it'd be a no dispatch item. Your parachute would have to be something that you can't leave without. So that would be another, not impossible, just another challenge to installing ballistic parachutes and using them as a solution to crashworthiness. So so in the future, really, what we'd hope to see is really defining with our operation and how we fly these vehicles, also our failures and our failure scenarios, and how that's going to define an emergency landing. And it's really based upon how it flies, how it's configured, and the loss of power, loss of thrust, system failures. The real dangers again are the transient phases of flight, the horizontal or purely vertical thrust. You know, if it drops like a helo with no vertical airspeed, or with a fixed wing airplane, you can be fixed in the air and you may not have any horizontal airspeed. You kind of hoped it glides in like an airplane, but you got to have that airspeed. You have to have enough altitude to do that. So it's really, I guess, what I'm after. What we're kind of hope to see is that in essentially all of your failure scenarios, you're going to be able to bring this aircraft down somehow under control to some degree to some sort of survivable landing. And it's tied to the unique design of the aircraft. So talking about crashworthiness pulling forward or going forward, how would we use this once we define our emergency landing? So obviously, if you could bring it within the existing parameters, then we could probably leverage Part 23 and 2027 crashworthiness and make it a lot easier for everyone. But if you have something that comes down that deviates from really the known, where we know our general crashworthiness works, then you really probably need to demonstrate some sort of equivalent occupant survivability. And again, these don't necessarily correlate directly to 562 and 561 loads, because there's airframe attenuation. But then again, we really don't. Airframe attenuation is generally, in current crashworthiness, is really not something well defined. We don't really take credit for it in traditional crashworthiness. It's just we have these points that are our targets on charts like this, that way back in the preambles of our rules, that we pick these points in space and we take this load at a floor and run a seat on it, and we really care from the floor up. We haven't traditionally, beyond dynamic seat testing, haven't really looked at the airframe like we kind of hope to look at going forward, which brings us kind of back to this holistic crashworthiness that Lowell had talked a lot about, coming back to the best practices. We want to build these features early into the airframe and design, and these are going to get us the best range of outcomes, probably in a lot of those crashes in that chart and the slide before. crushable energy absorbing airframe. This is all about creep. If you're familiar with that, it's just packaging a product. We want a rigid cabin structure, solid restraint attachments. They need to stay attached to the aircraft, the gimbal and your restraints and your seats. And they need to be able to gimbal as the airplane does deform upon in an accident. And we need to look at our head strike envelopes, make sure we can avoid hazards inside that the occupant might hit. Restrain items of mass, of batteries, of power plants, of cargo. So this brought up another interesting question. So a lot of this stuff is being brought into some holistic methods of crashworthiness that are being brought into Part 23 aircraft in the ASTM standards. These concepts are being brought in, and all of this is being brought in as maybe a little broader way of crashworthiness, not just a dynamic seat test and call it good. And which brings up an interesting point regarding items of mass. So we have, if you go back, we have in Part 23, we have a 18G requirement for items of mass. Now we start looking at some of these really large batteries. In a lot of cases, for CG reasons, they're moved after the cabin. So yes, we have an 18G restraint requirement for the battery itself, but we also should probably consider, what does that 18G look like with respect to the passenger cabin? If your 18G battery is restrained within the local structure, that's great. But if it starts to crush the cabin, I think we kind of missed the point here. So that's another thing to consider that actually has come up fairly recently in some discussions, that is an item of some concern for some of the generalized crashworthiness here. And again, we're going to look at minimizing post-crash fire hazards like battery. What's your battery going to do in the case of an impact? Normally, it was fuel tanks, how they would crack open, but we'll look at that, and then they all need to be bounded by a defined emergency landing condition. And one other thing I might note, I know there are some requirements out there, but you might keep this in the back of your mind as we go forward, is what kind of first responder rescue features you have in your aircraft. Because Tesla, a lot of vehicles usually have crash design guides, a lot of cars. It'd be a good idea to do that for aircraft as well, because firefighters will have a good idea of a crash design guide. If you go look at, like, for example, a Tesla has public documents you can go look at. They're really actually pretty cool to look at. They have a lot of features, or they have drawings of the cars and where to cut wires and how to make them safe and how to respond to them. And a lot of this stuff has been done by NFPA, National Fire Protection Association, and they started out on this about 10 years ago. And incorporating those things up front is a good idea as well. So you might take a look at that, keep that in the back of your mind as you go through developing vehicles. Final thoughts. Obviously, we move. The government moves slowly. Traditionally, our CERT moves ahead incrementally, and level of safety is based upon the best knowledge we have now. That's really what we're doing with eVTOLs. It could be better. We'd like to tune it a little better and make it a little broader, but we are where we are. 23 and 27 are being applied. We'd like to see the failure hazard analysis. FHA is being dragged into some crashworthiness scenarios, but so we have a good idea how eVTOLs would land, and then we can work from there on crashworthiness. And I would mention, I think there was a little talk of it before. Actually, there was a question before. Don't bet on eliminating crashworthiness if your FHA hazards are really small. There will be accidents. There will be a baseline level of crashworthiness. So we can't make them go away with really small numbers. New avenues. Other ways we could taking this forward. Other paths, there's the automotive paths. We discussed it earlier. There's the other, like full vehicle crashes. We just don't build enough vehicles. I know we talked about that before. That'd be a great way to do this. Maybe in the going forward. Modeling as well. Modeling's moving forward pretty well. Anyway, the further we go, the better results we have. We're just kind of out the gate here, so we really don't know what we have to work with. We don't have a body of data to work with. So, but either way, we can't really get there without bounding the emergency landing condition. So, anyway, that is all I had.
All right, thanks, Bob. So we probably don't have time to get into too deep questions, but I have a real quick one that was asked before. So if an applicant or someone's interested in engaging the FAA, who should they contact first if they have questions?
Well,
or how should they go about that?
There is early engagement on a lot of this stuff, and it's probably really good for crashworthiness. Early engagement is through P&I, the Policy and Innovation Branch, and I could probably throw some names out there. But,
right. And then your contact information was on the title slide, or for those that are listening, if you need to contact us, reach out to Bob and he'll forward you on to the correct office to help answer those questions.
Yep.
Yeah. All right. Well, thanks. And thank you, Bob. And we'll turn it over to our next speaker.
All right. Thanks, Joseph. Our next speaker is going to be Aiko Dune from the European Union Aviation Safety Authority, EASA. Aiko started his aviation career as an aircraft mechanic, working mainly in small and medium aircraft. He studied at the University of Stuttgart in aeronautical and aerospace engineering with majors in lightweight construction and systems engineering. In 2007, he moved on to the German National Aviation Authority as a structures expert in the field of certification. And since 2012, he's working with EASA as a structures expert located in the eVTOL department, being responsible for various rotorcraft, eVTOL, and rulemaking projects. Aiko, all yours.
Thank you. Hello, everybody. I'll try to bring up the presentation. Yeah, that'll do it. So yes, I'll talk a bit today about during the Rotorcraft Symposium. There is one on the 12th of November, a virtual one. There we meant to have a bigger workshop, the European rotors, which we had to cancel or we have to postpone due to the COVID crisis. But there will be a virtual event with some dedicated presentations for VTOLs. So how did EASA approach all this? We developed a special condition with the objective to put down a level playing field. So we wanted to have a defined way to certify those VTOLs, and it should be available to everybody. So we wanted to have it with an adequate safety objective for PACs and third parties on the ground. And in the special condition, we also wanted to use take some advantage of the higher redundancy you have due to the multiple lift thrust units. So the decision was to make this special condition where we incorporated elements of CS27 and 23. And we decided to make it performance-based. So it's similar to the CS23 Amendment 5 or the FAR 23, the performance-based, the newest one. To also adapt or to make it possible for a great variety of designs to not be too prescriptive, but to give the opportunity of certifying with this special condition all vehicles that come on the desk. And in order to make it more specific, we developed means of compliance for this special condition VTOL, which is sometimes based on current CS27 or 23 requirements, and but there are also entirely new things, especially for systems and fly-by-wire. So it's a mix of everything, but the means of compliance are meant to explain better how to show compliance to the special condition VTOL. But it also gives you the freedom to not do it in accordance to the means of compliance as we published it, but to propose your own way of certifying it. And it's not finally done yet, so we will supplement it in the future to address other things like remote piloting or autonomy, but we now focused on the current projects that were known or proposed to us. It covers everything up to 9 pucks and a bit more than 3 tons in a special class. So we tailored it firstly to the need there is out there now, and with the option to change it later on. So where are we with our special condition and means of compliance? The special condition was published last year, mid of last year, 2019. And then we started to work on the means of compliance in order to help the applicants to comply to this performance-based high-level objectives written in the special condition. They were presented, the first set of means of compliance we presented during the Rotorcraft Symposium. We took what we thought are the most important ones, and also the industry demanded what do they need to know right at the beginning. So we concentrated on them. This is public. We published them on our website mid of May for comment. We received then 761 comments. We are at the moment progressing in answering all those comments and then preparing a document in answering all those comments, and then also updating our proposed means of compliance to take into account a lot of the comments we receive. And end of this year, during this Rotorcraft Symposium, we will also present a second set of means of compliance, which we are working currently to be published, hopefully next year somewhere. So what is the overall approach of EASA? Well, we decided to have 2 categories, a basic one and an enhanced one. The basic category is operation over non-congested areas. So if you take off, fly over non-congested areas and you have an issue during flight, then you are allowed to do a controlled emergency landing immediately. Whereas if you go for category enhanced, that's what you need if you want to operate over congested areas. You need a higher reliability. So whenever you fly over congested areas and something happens, there are 2 opportunities what you can do. Either your system is good enough that you can go on to your final destination, or you have an alternate landing port somewhere where you can divert, but it's not acceptable to make a controlled emergency landing over congested area. So to wrap up the 2 safety levels, it's category basic, which is quite analog to CS23 level 1 to 3, so the low end normal category, traditionally called normal category aircraft, but a bit higher because new technologies like fly-by-wire are used and you can do a controlled emergency landing. Whereas when we go to the category enhanced, we moved forward on doing it in accordance with CS27 Cat A, or what was known in the old days as more the commuter category, CS23 level 4 aircraft. So you have to ensure continued safe flight and landing if you have any problems. This is an overview of the safety levels we developed. So it's for the basic category, this is the yellow category, goes from if you only have 1 pucks, you can go 10 to the -7. It goes up to 10 to the -9 for 7 to 9 pucks. If you go for category enhanced, then you always have 10 to the -9. catastrophic event. So this is the rough overview of how we try to handle the special condition VTOL or the VTOL certification. Now going in particular a bit to the crashworthiness requirements. In the special condition VTOL, we have 3 paragraphs that deal with crashworthiness. We have the numbers, actually you might know from the FAR 23 or CS 23. The 2270 emergency conditions, where it says that the occupant has to be protected in case of an emergency landing. Then we have another one, it's the 2325 fire protection, where I will go in further down in the presentation on the post-crash fire and post-crash hazard protection. And the third one we have is the 2430 energy storage. There it talks about that your energy has to be retained under any survivable emergency landing. All those 3 go together into the crashworthiness requirements we have currently. And for those, I go a bit more in detail. So the emergency landing 2270 is protection of each occupant against a serious injury when using all the safety features, experiencing the static load criteria, and it must include dynamic conditions and also in your baggage compartment, no shift of large masses, and you have to protect your flight controls, any wires. So that is the requirement, the special condition requirement for emergency landing. The second one we have is for the fire protection. So it talks a lot about minimizing the risk of fire initiation due to system failures, flammable fluids, oxygen system, and it also incorporates the minimization of fire initiation due to a survivable emergency landing. And this is then mainly focusing later on the fuel tank crashworthiness. And it also talks about minimizing the risk of fire propagation, but it's not directly linked to crashworthiness, so I go a bit faster over this. So for our means of compliance, the basis we took the CS27. Why? Well, the VTOL can be operated in a similar regime to a rotorcraft, so you have vertical takeoff and landing. But you also have, it can be way more diverse. The speed range could be much wider than for current rotorcrafts. You might have VTOLs with CTOL, conventional takeoff and landing capability, which then brings more the fixed wing world into play. But as already the speakers before me said, do we know how they really crash? No, we don't. So we have to make a best guess and look what we have, and we go forward now with what we have. So it's the 27561 for emergency landing condition, 562 for the dynamic conditions, which is more or less known as the dynamic seat test. Then we also take into account the 952, the fuel system crash resistance. That's the fuel tank drop test. And if you have CTOL capability, it is complemented by some CS23 rules. Some of this you probably will recognize that it's the same as the FAA, which is quite good that we go at least the same path there. But in order to show how we developed it and how our thoughts are behind this is a little history of how the crashworthiness was done. A lot of things came out of this one report done in the 80s, where more than 1,000 rotorcraft accidents were looked at, and it was looked at how did they crash and what speeds, vertical speeds, horizontal speeds they did crash, and what was survivable, what was not survivable. And based on that, all those 27 561, 562 rules were developed. one of the charts I like in it is this one where you have on the y-axis you have the impact velocity in foot per second, and on the x-axis you have the cumulative frequency of this potentially survivable crash. And based on this, there has been put down the line 95%. So the static and dynamic crashworthiness requirements out of the 27, they come out from 95% of the crashes should be covered by those static and dynamic crash conditions. And there has been an additional safety layer for the fuel tank crashworthiness. It's something around about 50 foot per second, which covers more than 99%. So to summarize those two crash scenarios, so we basically have two layers of protection. We have what's also referred to as a minor emergency crash landing, with this 30 foot per second impact velocity. And the loads on the seat for rotorcraft should not exceed 30 G on seat attachment level. That's the typical dampening structure you have underneath a helicopter. And the important thing is for this minor emergency landing, the occupant must be able to evacuate themselves. So they should be protected from any serious injury which might hinder them to evacuate themselves. Whereas the second layer of protection is the 952, the drop test, where you drop the fuel tank from 15.2 meters, 50 foot. This exceeds deliberately 99% of the impact velocity envelope, which we just seen. But this is a survivable, but as an occupant, you will have some injuries, maybe even severe injuries. But this is mainly written to protect the occupants from any post-crash fire or post-crash hazard. So we definitely want to rule out that an occupant survives and then afterwards gets killed by any post-crash fire, post-crash hazard. So the outcome of those two layers of protection, this graph you have already seen from Bob in a bit different way, but the outcome is the same. So we take the 27561 loads. If you have CTOL capability, then we include the 18G forward instead of 16G forward. So again, you take the worst of the worst. But this, and also for the next slide where we have the dynamic conditions, these load factors we see only as valid if the structure, especially for the vertical impact, the structure underneath the seat has equal or better dampening characteristic as a conventional rotorcraft. Because when you imagine you screw your seat on a seat rail directly on the ground without any dampening structure underneath, then the loads will be much higher. And those 30, here it's a downward 20G, or here we see the velocities or the G loads for the dynamic seat. If we have a different dampening structure underneath the seat, this might not be a valid assumption, having the 30G. It might be more if you don't have any dampening structure underneath, or it could be even less. So we are, even with this MOC, with the special condition, we only put a very objective-based requirement anyhow. But also this 30G downward, for example, is not written in stone. But we try to get the same level of safety as you have today in the rotorcraft. So we have to somehow, out of this impact velocity that was shown in the graph before, this 30G was derived, taken into account a dampening structure underneath the seat. And this has to be also valid for new design concepts. Then we move on forward to the energy storage drop test. So energy storage, we use this word, I think also in the means of compliance quite a lot in order to get away from the fuel tank requirement. In VTOLs, traditionally at the moment, you don't have any fuel, you will have batteries. Maybe in future it will look different, so we try to write this drop test in general for any fuel or energy source you might have. So it is based on the 952, which I just said, 50-foot drop test. And during this drop test, or the aim of this drop test is to minimize the hazard in any survivable crash landing, which is the 50-foot drop test. I tried to write it to address liquid, gaseous, and solid energy storage systems. I know that at the beginning it will be most likely the battery one, which is looked at, but still I wanted to give it a wider thought, and especially not lose the content which is currently in the fuel tank crashworthiness. And like in the fuel tank crashworthiness, you have to have self-insulation means. For electrical, it needs to be an automatic insulation means, which is requested in order for after an survivable impact, we cannot assume that any of the occupant or pilot is able to shut down the high voltage. So we request that this will be done automatically in order to protect the people when they try to escape from the vehicle, or when any rescue personnel comes and try to rescue somebody, that we don't endanger them by high voltage. The TOS condition is traditionally, and it's also set in the 952, it should be tested in a representative surrounding structure. The fuel tanks normally have been dropped in a bit of surrounding structure, normally taking the structure underneath a bit forth and back. Everything which could cause a leak is included, everything else not. But we saw already, or we had already the question and the discussion if also a full-scale drop test can be done. And we don't see any reason for not doing it. The representative surrounding structure is not limited to any size. And this is also a thing we are discussing or already got proposed to do it also for the seat testing, to not make a 30G downward seat testing, but instead making a drop test with a impact velocity which corresponds to this curve I showed earlier, 30 foot per second, and then show that the crash test dummy will not exceed the prescribed loads. So this is also something we look into, we don't rule out, and we are happy to discuss with the industry about it. So you don't have to drop the entire energy storage system, but at least the most critical one has to be dropped. It must be filled or charged to the most critical condition, which also includes that you should take into account temperature if it's critical for your energy storage. For batteries, normally it's more critical if you drop them at high temperatures. Then you should also take this into account. You have the 15.2 meters, you drop it freely on a horizontal surface, plus minus 10 degrees. This is pretty much taken out of the 27952 requirement. Pass-fail criteria. For liquid or gaseous fuels, we took the pass-fail criteria directly from the 27952, no leakage or flammable fluids or gases after the drop test. In the AMC material or AC material, it's set for 15 minutes. This must be free of any leakage. For batteries, we discussed with the industry a lot about this, and when we wrote it, the first my first approach was to say, okay, structural damage should not lead to any fire, leakage of harmful fluids, fumes, or gases. Then a lot of industry came to us and said, well, that might be a bit difficult to achieve. So we discussed, and we included a second requirement or a second possibility to say, okay, fire or leakage of harmful fluids, fumes, or gases is allowed, but it should be contained for at least 15 minutes in a non-occupied area outside the evacuation path, in order to allow for rescue personnel to arrive and to rescue any occupants before the fire or fumes, gases are becoming a hazard. And in addition, this is the main thought was for pressurized energy storage systems, that any projectile release should not lead to serious injury to occupants or persons on ground if you have a high pressure energy storage system. The last one we talk about today is the battery drop test for overwater operations. This is currently in a draft status, but EASA is always trying to be as open as possible, and we always want to let the industry know what we are doing and also get feedback from the industry. That's why we are also willing to share this with you at this at this early stage, in order to also get your feedback on that. The requirement I already mentioned: retain the energy under any survivable emergency landing. This is for fuel tanks, you don't have it, because a fuel tank, it doesn't matter if you drop it on water or on land. Even on water, it's probably more, it's less critical. But with electricity and water, it could be a danger for the occupants and for rescue personnel. So you want to protect them from high voltage after an emergency landing on water. So what you see now is the draft that we are currently discussing internally. If you want to know more of it, on the 12th of November during the Rotorcraft Symposium, we will present a bit more about it. But the idea we currently have is to have 3 layers of emergency landing on water. The ditching one and the emergency flotation one is equivalent to the one taking out of the rotorcraft. It's if you're a certain amount of minutes away from land on hostile sea or non-hostile sea. And what we additionally did was we developed a third category with limited overwater operation. This is when you are only a limited time away from land, then you have to fulfill less requirements. For crashworthiness, this means we have, I already mentioned, those 2 layers of protection on this curve, the 95 and 99% curve. And for this limited overwater operation, we have the thought that it might be too stringent to demand a 50-foot drop test, taking into account the limited time you're operating over water, and therefore it's more unlikely to have an emergency landing on water. So we, at the moment, the proposal on the table is to take a 97% curve in order to make sure that if you have this drop velocity, that there will be no release of energy, high voltage, after a crash landing. In a table, it will look like this. You have the operation on water, ditching, and emergency flotation. You do a 50-foot drop test. If you only have limited overwater operation, we are currently thinking about 6-meter drop test height, which will correspond to this 97% curve. But remember, this is all under discussion and under draft, and we will conclude on it later. And but if you have any thoughts about this, you're always welcome to contact us. And the last point I want to raise is the ballistic recovery system. It was already mentioned by Bob. Yes, we certified it for 23 aircraft, only if no suitable landing sites are available. We did it always on no credit, no harm basis. For VTOL, we have a you are operating very much above congested areas, and you don't do this with traditionally with CS-23 aircraft. So I also see the danger with this BRS if you use it instead of crashing also over congested areas. It's good, but if you pull it too early, or if you are too low, then it does not give you any benefit. So we will definitely not prohibit you to use it, but we have to discuss how much credit we can give for it, and how much you still have to take other things into account. So this is it from my side. Thank you all for listening, and maybe there are some questions.
Yes, Heiko, thank you. Very good presentation. There are two. Let's see if we can get through them real quick here. The first one says, new technologies like fly-by-wire serve to enhance the safety by providing protection against pilot error. Why further raise the safety bar by increasing the DAL requirements for the technology that in and of itself increases safety? Isn't that undue burden on the applicant?
I'm afraid I'm the wrong person to ask that. I'm a structures expert. Our systems expert, I think, can better answer this question.
Okay.
But I think it's yes, it's better than the pilot, but still you want to ensure that it has a proper safety level. And I think the proper safety level established is this we mentioned. But if anybody wants to talk about it more, I think our systems people are the right contact.
Okay, and I'll give you one more here, since this looks more like a structures question. Will the applicants be able to demonstrate the 30G equivalent damping behavior has been achieved by, and it says MOC 4 or is MOC 2 sufficient? And I assume those are two means of compliance.
Yes, it's by either by partial test as MOC 4 or by analysis MOC 2. It has up to now we always assumed we never, or Bob already said, we never took into account the structure at all. We basically assumed that it's kind of the same as it was thought of. So I don't think we want to have somebody dropping rotorcrafts in order to compare it to their VTOL. I think an analysis will be sufficient here to show not that you're at the 100% the same, but that you are in the same range as a normal helicopter, and also not to invalidate the assumptions.
All righty. Well, thank you, sir. Appreciate it.
Thank you.
I'm going to turn it back over to Joseph, who's going to introduce our last speaker. Joseph?
Yeah, thank you. Our next speaker is Eric Nautar from Bell. Although he's with Bell, he's going to be here today representing ASTM, and he's going to discuss using the ASTM F44 as a means of compliance for Part 23 and some of the work that's ongoing there to support eVTOL. Eric is an administrator and structures unit member in Bell ODA and supports Bell Innovation Team certification efforts. He's also the technical contact at ASTM F44 working groups that are evaluating the incorporation of eVTOL aircraft into both emergency landing conditions and bird strike standards. He has his BS from Purdue and his master's and PhD in aerospace engineering from Texas A&M. In addition to his engineering interests, he's also an ATP-rated pilot, flight and ground instructor, and a licensed A&P mechanic. So kick it off to you, Eric. Thank you.
All righty, Joseph. Thank you very much. Hope everybody can hear me well. I want to thank both you and Justin for putting together this workshop. It's a tremendous opportunity to have everybody get together and bounce ideas off and actually move the technology forward. And thank you, Chris, for all your work with putting together the conference. Today, I'm going to talk about some of the ASTM F44 activities for means of compliance for Part 23. I'll start with introduction to ASTM, talk a little bit about different standards, and then pass for eVTOL certification, and then go towards occupant protection, and specifically focus on 2270, which is emergency conditions. And then speak a little bit about what we think about when we're developing a new standard. What do we need to do? And then, of course, we always welcome participation from all of our audience and friends and interested people. What is ASTM? ASTM International is a huge organization that essentially works on developing standards and best practices. It's been around for quite some time. It was established in 1898. It's got 150 committees, over 12,000 standards, and over 32,000 members. And it's not just an American company, it's an international company, and it's something that always considers the interests of both users as well as manufacturers and things. It's accredited by several groups. It's ANSI certified, as well as the Standard Council of Canada. And you might ask, what's the benefit to using the ASTM standard? Well, if there's an ASTM standard that is accepted by a regulator, then the individual projects and individual people that are applicants, they don't have to spend their money developing standards and working for ways that might be acceptable means of compliance. So it really doesn't add cost to particular certification projects for the applicants. What type of standards are there? There are various types. There's a company standard, where a company might put something together for an individual corporation. There are consortiums where they might be a small group of organizations or companies. There are industry standards for many companies. There are government standards, and then there are voluntary consensus standards. ASTM is in the activity of developing voluntary consensus standards. The strength of this is that you really have representatives for all sectors that have interest in using this standard. That includes both participants that are interested in it, users that actually intend to use it, as well as manufacturers that are tending to develop products that will be used with that standard. And since they have such a broad input, a lot of the times they're considered the most technically sound, and they're often used for a basis for both commercial and regulatory action. In the following standards in ASTM, the committees were joined for aviation. One is F-37, which concentrates on light sport aircraft, which are aircraft that have a gross weight of less than 1320 pounds unless they're an amphibian. F-38, which is unmanned aircraft systems, which really started out as something for small unmanned aircraft systems, but has actually matured to and is actually handling things that exceed Part 107 guidelines in terms of gross weight. Committee F-39 is aircraft systems. Committee F-44 is general aviation aircraft, and Committee F-46 covers aerospace personnel. So with this, you see, you're really covering a very, very broad area of aviation activities, and thus standards which reflect ways that you can comply with the various regulations, and also as guidelines which help you develop things. One thing nice about the standards is now that we're moving to, in Part 23 and CS Part 23, performance-based standards, there was a rewrite again in 2017 that the intention of that was to actually try to future-proof the regulations from future technology development. So instead of having something that was extremely prescriptive that said you would do certain things in a very well-defined way, it would actually have end goals that you would have to achieve and actually have openings that you could have for the different developing technologies that could achieve those. And industry standards were a very, very key part to that development. And ASTM developed the F-44, which was the General Aviation Committee, to actually work on means of compliance for Part 23, Amendment 5, and CS23. And again, you were looking at regulations that were performance-based, and they had a safety intent, yet the standards would be able to go ahead and capture the new technologies and methods that you could meet those requirements. One thing is, most people know to develop new regulations. It typically takes 3 to 5 years, which is quite a bit of time. And at the pace of the ODM development that we're having with a lot of the eVTOL aircraft, it is developing at an extremely fast pace. And we thought it would be a great mechanism to have means of compliance that actually could be very dynamic relative to the regulations in terms of development. And they would be able to take care of the, and actually encompass some of the new technologies that would meet those performance-based standards. One thing that we also need to remember is the eVTOL aircraft really were not envisioned when F-44 was developed. And it's something that we're now working on different ways of incorporating the eVTOL aircraft into those existing standards, or possibly developing new standards to act and be approved or accepted as means of compliance. Now, in 2019, there was a study that was done to say, well, what's the applicability of the current ASTM F-44 standards to eVTOLs? And the outcome of that study was that about 67% of them were pretty well applicable as written. But then we needed other things. For instance, there was 13% that required modification or additional sensible standards on there, some that needed major modification, and maybe some of them weren't applicable. So again, that was a 2019 study of that. Now, when we start talking about a quickly evolving world, let's talk about the Part 23 accepted means of compliance. Just recently, and that is September 22nd of this year, there was a notice of availability published in the Federal Register on September 22nd for the acceptable means of compliance for from ASTM that would be applicable for Part 23 aircraft. And with that, 65 regulations were covered by ASTM standards. 42 of them were accepted as is, and then 23 were accepted with changes or supplements. Bear in mind, that was Part 23 in a normal category of aircraft, not necessarily eVTOL applications. Now, when we start talking about eVTOLs, there's a little bit of a paradigm shift. When you start talking about a lot of the eVTOL certification requirements and some of the stuff that's a risk-based type system, both operation as well as the certification of the aircraft get closely related to the eVTOL aircraft. And there's really a sort of a trade space between what the aircraft can do, where's the human in the loop? We talk about some of the stuff where we have unmanned aircraft, autonomous aircraft, simplified vehicle operations, and each one of those has a various level of human involvement in the operation. So in terms of aircraft certification, the committees F-37, 38, 39, and 44, which are essentially the aircraft performance standards that would be for small aircraft or the unmanned aircraft, general aviation aircraft, and then the different systems involved are applicable. When you start talking about the airspace and integration, both the general aviation and the unmanned systems aircraft would be applicable. And then when we talk about operations, F-38, which again is the unmanned aircraft, as well as the aerospace personnel are applicable. So what we do is we really are kind of looking at something where, depending on your operation and depending on your aircraft, standards developed by either or many of these committees could be applicable. In addition, in terms of actually addressing the eVTOL needs, there have been several advisory committees that have been developed. One is AC 377, and the focus on that is on autonomy, and that's going to be for all aspects of aviation for both the small unmanned aircraft systems, as well as the general aviation and unmanned aircraft. And one of their activities recently has been they put out a report in 2019 talking about levels of autonomy for the aircraft systems based on the automotive style autonomy. And they're now working on guidelines for technical pillars of autonomous systems. Another group is AC 433, and what the focus of that group is to fill gaps in existing standards for both eVTOL and UAM aircraft. And that was established, and the first meeting was in 2019. And really what the goal of that committee is identifying and scoping gaps and then working with the different technical committees to try to fill them. Now, F-33, which is a small aircraft committee or unmanned aircraft group, as well as the F-39, which is the aircraft systems committee, are both active. F-38 is working on the UAS technologies that can be applied to UAM. F-38 is also working on the design aspects of vertiports. And then F-39, which is systems, is looking at electric propulsion system components, energy storage systems, et cetera. And then F-44 is looking at distributed hybrid all-electric propulsion integration flight controls, as well as flight and performance standards and other alternative approaches to system safety. Now, when they've done some analysis, some of these are not going to surprise you. Things like electric propulsion system design and installation, or electric propulsion units design, or storage systems are not surprising. It's something that we're using new technologies in the aircraft. But then we also have to consider things such as emergency conditions and bird strike and handling characteristics and performance. Another thing on there, which is a topic that is of very, very high interest, is simplified vehicle operations. When we're talking about eVTOL aircraft, in order to actually meet some of the marketing demands and projected forecasts, we really are going to get into a situation where we're going to have a shortage of qualified pilots. When you start looking at some of the qualifications for Part 135 certified pilots, you're talking about, for, say, IFR type pilots, a 1,200-hour pilot. And up until recently, that was a very, very tough commodity to get. There's a lot of competition, and it's been for the airlines. And a lot of times when you start looking at the cost models, the airlines could probably afford to pay them a little bit more. Now, temporarily with the COVID crisis, there's been a bit of a switch. We'll have to see how things happen. But even with that, the goal of the SVO, Simplified Vehicle Operations, is to reduce the complexity and a lot of the training and skills required of operators for some of these systems when you start going towards higher automated or fully autonomous systems. In this talk, we're talking about crashworthiness. So things that would be interested for occupant protection would be emergency conditions, bird strike, as well as energy storage. Particularly, we're looking at emergency conditions. In terms of certification, if you have a eVTOL aircraft, and I'm going to talk about the FAA certification path at this point, there are really two different methods that you can go to certify it. And one of them is 2117A for existing classes of aircraft, and the other one is 2117B, which is special classes of aircraft. And both of them are essentially derived from parts 23, 27, as well as part 33 and 35, which are the propeller and power plant type regulations. But the difference in them is really the protocol that is used to certify the aircraft. So when you certify aircraft, when you're looking at developing a certification base, it is often a function of risk identification, functional hazard analysis, and mitigations. So when you're using a 2117A approach, where you use existing parts 23, 27, or 33 and 35, we can typically use 2116 special conditions that are derived from other parts or new requirements for some of the technologies. If we go 2117B, we essentially have to have our entire certification basis vetted in Washington to go ahead and have that approved. Again, the end result is the certification basis for the same type of aircraft should be essentially the same, because for the same configuration of aircraft and same use, you essentially have the same risks, and this should have the same type of mitigations. In terms of occupant protection, there are existing requirements, and this is some of them. And we focused on, of some of them, not a lot of them, on the energy storage aspect, which typically in the 14 CFRs and the 900 series, or at least in Part 27. But we looked at Part 23 and Part 27, which is airplanes and rotorcraft, as well as eVTOL, have existing requirements in there. Looking at them in terms of crashworthiness requirements, some of the common things we're looking about is emergency conditions. And again, specifically, we're going to actually focus on 2270, which is emergency landing conditions. When we pull up 2270, we see that the airplane has to protect the occupants for various things. First of all, they have to have the right safety equipment on. And then you have to include both static and dynamic conditions, protect the occupants for likely ground and emergency landing conditions. And then everything must perform its intended function and that could cause secondary injury to the occupant. And you have to also consider baggage and cargo compartments. One thing you notice when you look at this is that we worry about flight and ground load conditions. What are they? That's something that both the presentations from EASA and the FAA have said that we have conditions out there existing for Part 23 and Part 27. And for VTOL, what are they? And that's a big question we have to ask. And the question is, are the requirements that were specified in 23.561 and 562, again, this is an amendment 62 prior to the performance based in 64, or 27.561 and 572 appropriate? Very good question. That's part of our task to determine. Well, currently we have ASTM F3083, which is standard specification for emergency conditions and occupant safety and accommodations. When you look at that standard and you look at the history of it, it was developed for fixed wing airplanes using FAA 14 CFR Part 23 requirements and guidance. When we start looking about eVTOL aircraft, we need to consider what are the consequences of having VTOL aircraft operate. Some of the things we think about is they're going to be higher vertical loads during emergency events, i.e. thrust failures during takeoff, climbs, descents, and landings for all phases of the VTOL flight operations. Another thing is a lot of configurations are going to have mass items that are located both above and behind occupants that could cause injury if they weren't contained. Another thing that was pointed out is we've got higher demands on the landing gear for energy absorption during vertical descents compared to some of the conventional takeoff and landing aircraft. And then and I say least, not to be last but least, the potential energy storage hazards, including the petroleum fuel, if you have a hybrid vehicle, need to be considered. Well, with that in mind, ASTM Working Group 68781 was established to evaluate the applicability of the current F3088 standard for aircraft with VTOL capabilities. Next thing we'll ask is, when you're developing a new standard, what do you need to consider? Well, considerations for the landing loads are, you've got to say, what are the landings going to look like? What are the emergency landings going to do? Are they similar to the aircraft or are they new? If they're similar, you can use conventional airplane and rotorcraft data, which exists, determine the loads using the historical data, and you can specify the loads. If you have unique characteristics, then no data exists, and you've got to approximate the conditions. How do you approximate them? There are two different ways of doing that. One is to develop new loads, and the other one is to use existing standards. Now, there's a little bit twist of a chart that some people have seen. When you start looking at some of the existing conditions, they were all based on accident data. What we were looking at is a 95% probability of survival. So there were studies, and they've been overlaid here to say, at the 95% survivable rate for an accident, what type of velocities do we see in the impact? So there were studies for both the Army, Navy, as well as civil. And we say that for rotorcraft, the descent rates range from, this is vertical descent rate, from 26 feet per second to 42 feet per second. And one thing that comes from that is it doesn't matter necessarily just whether it's a rotorcraft or an airplane. What matters is how do you operate it? For the static loads, one thing needs to consider what are the current Part 23 and Part 27 rotorcraft loads. And again, you've seen this type of data in a different format, but this tends to point out the various differences between airplane and rotorcraft standards at this point. For the occupants, you can see that for the forward loading, and the downward loading, the rotorcraft have a higher load criteria for the passengers. For the items of mass in the cabin, rotorcraft have a higher loading for downward, but they have a lower loading for the forward loading. And for items above and aft of the passenger compartment, you'll see that the rotorcraft have a high downward loading, but you'll also notice that the airplanes have a very high forward load required for mass retention. Now, one thing to be pointed out was that came about based on certification requirements of aircraft that had engines mounted in the fuselage. Another thing to consider is dynamic landings. When you look at both helicopters and you look at airplanes, you'll see something that's very interesting. In Part 27 and Part 23, you'll notice that in terms of the velocities, both the longitudinal as well as the vertical velocities are very similar. For a rotorcraft, the horizontal velocity is 42 feet per second, and for an airplane, it's 42 feet per second. And then for rotorcraft, the vertical velocity is 30 feet per second, and the aircraft is 31 feet per second. Not too much of a change. When you start talking about the acceleration loads, you find there's a huge difference. For airplanes, you'll see that for a longitudinal deceleration, there's a 26G requirement, but there's also something that for helicopters, it's 18 Gs. Now for the airplanes, they take into account some of the deformation and attenuation of the structure, and you'll have to notice that it's 26 Gs for the first row and 21 Gs for other rows. And the same thing for the vertical velocity. It's 19 Gs for the first row and 15 Gs for the other rows. So the question you have to ask yourself when you're developing these standards is, what are the eVTOL operations going to require? What are they going to look like? Now, in urban operations, they're going to be similar to rotorcraft because of some of the vertical takeoff and landing necessity due to the landing zones, but we don't know. So with that, I can say that we have several committees out there which are intending to provide guidance and answer questions. In terms of working groups for occupant protection, we've got the 68781, which I spoke about, which is emergency landing conditions for eVTOL aircraft assessment, which is intended to investigate F3083, which is standard specification for emergency conditions, occupant protection and accommodations. We have a working group 68805, which is bird strikes for eVTOL aircraft assessment. And again, that's intended for F3114, the standard specification for structures. And then we've got a working group 65629, which is for energy shedding and crashworthiness. And that is to investigate F3239, standard specification for aircraft electric propulsion systems. So there are a lot of opportunities out there, and we really would love participation from all members that are interested, both industry-wise as well as users, and especially an international flavor for everything. And with that, I'll turn it back to Joe.
Well, thank you, Eric. A nice presentation to kind of tie in together where industry is helping to support where we're going. Say separate from the regulatory part of it, as through the ASTM committee, are we considering a full-scale test as a possible means of compliance to demonstrate some of these concepts, or we're still kind of looking at following along the piece part regulations like we have now?
At this point, everything is under development, so we do have opportunities to help provide guidance and standards. I will say that it depends on configuration and a lot of other factors. So we certainly haven't ruled that out. A lot of the full-scale testing is extremely expensive too. So there are opportunities to consider things like analytical modeling, et cetera, too. So I can say that the initial work that we have done has been investigating current standards and paths forward, but that's certainly something that's open in terms of an option.
All right, thank you. And with that, we are actually just right on time, so I will turn it over to Justin for some closing remarks.
Thank you, Joseph, and thank you, Eric, and thank you all the speakers for presenting today. I thought there was a lot of good information presented, and I know the question that keeps getting asked is, will the presentations be available? And they will. They will be on the website, hopefully by next week. So check back on the same link that you got from Chris Clark, and those presentations will be uploaded soon. I thank you all for attending. I hope it was informative. As you can see, there's lots of design space. There's lots of designs. We're at sort of the beginning of this journey here, and so you know, there's a lot of opportunity to incorporate crashworthiness and especially innovate here. Couple logistical comments here. So we have saved all the questions for the speakers. We will go through the unanswered questions, and hopefully these will guide future discussions. As you've seen, the workshop today was primarily sort of a presentation based workshop. That's really just to get the information out, to sort of start to get some awareness from the general public. We're planning on 2 more of these, intentionally spaced out. The next one probably be in December, but we want to keep sort of shorter presentation or shorter workshops, but you know, being able to ask speakers under you know, various portions of the eVTOL world, and so we sort of group them together. So the next session we're targeting is for December. If you have your contact information either on the polls that was created today, or if you've been receiving emails already from Chris Clark, then you'll be on the list, and of course she will send out information regarding the next meetings. We've been getting another question about you know, will we have some sort of interactive portion where, you know, it's more of just a group discussion? Yes, we'd like to. That is the intent, is to have that at our in-person workshop. Ideally next year. We're targeting maybe tying it in with VFS 77 or something like that. So really the intent here is to get all the information out so that everybody has all the information. When we come together, we can then have sort of a working discussion, and really to sort of you know, discuss these questions asked. We'll have the questions, identify gaps, identify, you know, maybe where we could be conducting some of this research or addressing some of these issues in order to sort of make this a full experience here. So if you have any other questions, feel free to contact me or Joseph. Our contact information is on the website. If you have questions for the speakers, you can contact us and we can pass along the information. Otherwise, I think the speaker information, contact information is on their presentations. If it isn't, we can get you in touch with them so that you could have further questions answered by them. So with that, I think we're going to sign off. Everybody have a good day and a good weekend, and stay tuned for announcements on future workshops. And we will hopefully see you all soon.